And we are live. Okay, great. Welcome everyone to today's live stream. We are doing Hyperedges and the Nodiverse. Or is it Nodiverse? We shouldn't confuse those two, I guess.
Welcome everyone to another life science session. As you might remember, we are in the business of formalizing our hypergraphs once and for all, hopefully. Last week, you heard from us from Paris. I was there. We were running the Hypermetrics workshop, and if you might remember Nikolay's talk, or you know of his work and his research group sort of efforts, specifying exactly what the data structure of a hypergraph is and how rewriting applies to it is extremely important. We ourselves, Nick and I, in developing many of the functions, we're reusing some physics project functionality, but also trying to introduce some functionality that was based more on labels. And, it got to a point where it was a little bit confusing. And I think, and on top of it, we had the problem that everyone's trying to solve. And this was also seen last week at the workshop, of mixed symmetry edges and how to deal with canonicalization of hypergraphs when you have several kinds of symmetry in each edge and how to encode that information and so on. So I'm happy to announce that, I don't know if it's an actual announcement that will have any impact, but I have a proposal of how to do this now. Steven seems to like it. We've discussed it a little bit. So this is going to be my sort of trial run with Nick and you, James, and let's see how it flies. So unless there's anything that you'd like me to say more generally, I can just dive into it.
So there's a bit of echo. I'm going to put my headphones on here. Sorry for the audience.
Sure, no problem. Screen one share. I think you should be able to see this stuff. I'm going to make it much bigger. Is this size okay? Okay. So, right. So as I was saying, we are at the moment of recasting what the foundations, how we understand what hypergraphs mean at all. And so I'm going to give a conceptual summary of how this is meant to be thought of. And then hopefully we'll get into some nitty gritty of even the canonicalization question and so on, which is what we really have to do next. So conceptual summary, so what I want is something that is clearly, conceptually, that everyone can understand what we are defining, that we can quickly explain what hypergraphs mean to us, that we are easily implementing in rewriting, and of course that we embrace sort of the causal analysis of multiple graphs as the main tool to make progress and compute within this framework. And of course, we should be able to account for all kinds of hypergraphs that are known in the literature, in particular, all kinds of hypergraphs that we ourselves have dealt with so far in more context of physics project, more in context of infrageometry, more in the context of higher arity algebra and abstract algebra and so on. Okay, so what's the idea? So first is the idea of a Nodiverse or nodes. Steven is suggesting that we call them EAMs. This is the physics project name, obviously, which are sort of atoms of existence, as he likes to call them. We might want to reserve EAMs for sort of infrageometry, or when there's an implication of geometry about these hypergraphs. But this is purely abstract or sort of computationally unbiased in some sense. And so the idea is that you should imagine just a set virtually infinite of just nodes that carry unique identities. So they have unique IDs. You can imagine that they are unique. They are almost like atoms that they are identical but distinct. That's kind of the philosophy here. Beyond their individuality, nodes are completely featureless. Like nodes themselves are just featureless. So if you want to have some sort of computational idea about them, make this a little bit smaller so one can read that. These are almost like memory slots, right? These are the places where your data is going to exist or is going to be supported on.
Right? Like an address. maybe?
Yes, that's Sorry, that's the word that I think we used last time, and I just forgot to reuse it. So yes, like a memory address kind of thing that can be populated as necessary, but it itself carries no information. So there's no real sense of creating and destroying nodes in some sense. It's just that you populate or unpopulate nodes, right? In this sense. Okay, so next thing is the concept of a bag. Simplest concept ever. This is exactly what everyone grows up to understand from their very early months of life. So this is just a collection. So mathematically, it's a subset of nodes because we define the nodes as a set formally. So these are just simply subset of nodes. If you want to evoke some past language that we've used or people use, these would be simple undirected edges. That's essentially what, if you think of the things as nodes. So these are just subsets of such objects. And the way to think about them is basically just a collection of memory addresses, right? So it's just like stipulating here, 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 and as you sort of highlight those and you sort of bundle them up. That's it. No more structure there.
And that's obviously you can't have a repeated node in such a collection.
No. Not repeated nodes. That's crucial. We'll get into the weeds of this in a second, but that's crucial. So I really like to emphasize, I love your question, James, because I really like to emphasize nodes are unique but featureless. But there's no notion on like cloning two of them, because then you will be breaking this axiom of them being unique, right? So they're distinct. They're unique and distinct, right? But otherwise featureless, which is a little bit maybe paradoxical to think about sometimes, that you really get into the details of what that means, but that's the idea. And really, the concept is easy to grasp as a memory address or something that is to be populated and can be, there's a supply of it in any given finite procedure or algorithm or computation process. There's a supply of these addresses and they can always be available, right? That's the sense in which it's virtually infinite, in some sense. All right. So bag is just a delineation of them. Is like grabbing some of them and just like sort of saying these bunch of them, right? Think of it as you will. You might want to think of them as sort of like selected memory addresses or like an order list of memory addresses. That's kind of the idea. And then the main contribution of this framework, or what I want to sort of propose or defend here today, is the concept of a spine, right? Or spinal graph. So the concept of a spine is basically, okay, so let me just give you a motivation for it. When dealing with data, we in our cognitive lives and our computational environments, we typically deal with sequentiality. There's a lot of processes that require some kind of sequentiality. I mean, least of which the fact that we have running time and the flow of time seems to be the source of this natural sequential structure. But so a spine is a sort of crystallized temporal information in some sense, meaning you want to give some internal structure to a bag. So you take a collection of nodes and you want to give some kind of internal structure. This is what we've referred to in the past as symmetry. That's why I say here symmetry relations between nodes. Specifically, we are thinking of this as simple connected directed graphs, but I'll get into the details in a second. But for now, the idea of a spine is some kind of information that is a predicate on the nodes that are in a bag that basically give them some internal structure, some kind of, it specifies some further structure than just the fact that they're all together in some bag that is unordered.
What makes it not a bag of bags?
So you could have a bag of bags. This is a fine approach, but for a spine, a generalized spine could be any collection of bags. And in fact, this is an interesting exercise to actually say, if only there could be bags ever, can I formalize all possible data structures? I have a sense that this is possible to do, and I actually did a little bit of that a year ago or so, like where I tried to define, which is similar to the Kuratowski definition of tuples, if anyone's curious about this. So Kuratowski's definition of tuples just said theoretically, if you only have sets, right, which are unordered, right, how do you get something that is ordered out of that? So basically what you do is you say, if I have the pair AB, so the pair, meaning the set AB to distinct elements, and I want to form a tuple, A, B, that A comes first from B. What you form is the collection of sets, A, B, and one subset of the two, for example, A. So if you have the set of sets that is A and AB, that has an asymmetry between A and B, and so that allows you to encode a tuple. So I think there's a similar game that you can play to define all manner of things, like cycles and bags and all these kinds of things, just with bags. But it felt necessary here because of how we are going to implement this in the first place, and the fact that we are going to be based on hypergraph rewriting or graph rewriting as a main computational framework. But it's perfectly fine to imagine that it could be hypergraphs within here, or just simply bags within here, and to have some nested structure there. But for now,
so it depends on what we're trying to do. I think is important. Yeah, like there's many ways you can frame it and how to create the information, but we're aiming in a specific direction with an intent.
Yes.
Yeah.
The point is that the specific direction I do think is extremely general. So it's not that, okay, this is one choice, but it could be many, but this is really going to recover. Because the idea is that you want an edge, I mean, just to give the full sort of picture of what we're doing here, an edge you want to be a data structure.
Okay.
Right. Sorry, it says bone here, should say bag. That's the better name that we have now. So an edge, you want it to be a data structure, because that's, I mean, so far, this is what everyone has dealt with. And I mean, this is there's no philosophical reason here why we want edge to be that status, but it's just historical, right? I mean, everyone's defined hypergraphs as either sets of subsets or sets of tuples. Mm-hmm. And, you know, in the physics project, they were basically just sets of tuples with order lists, right, as edges. More generally, people know about combinatorial species, which is the sort of more formal categorical treatment of general partial symmetry objects. So the expectation here is that so a combinatorial species, in case anyone in the audience is vaguely familiar with this theory, you would remember that a combinatorial species has the information of an underlying unordered list of elements, and then some symmetry information on how to permute those elements. So that's exactly why you need to think of edges as a bag plus a spine on that bag. And so just to reuse familiar language, a bag is simply a set. It's just unordered collection of unique elements, the vertices, the nodes. And the spine is a simple connected directed graph on that. We might want to drop connected and to explore some data structures, but for now, it is much better to actually keep them connected, because otherwise it feels a little bit weird. And you know, some algorithms will just not work as nicely as that. Okay, so most important. Okay, so this is somehow the foundation. So this is the data structure, the declaration, right? Now the actual data on these things is what we call a hypergraph. So specification of data on these things is what we call a hypergraph. So specifying data on memory addresses means that you have to populate the memory addresses. So the memory addresses are populated by labels, right? We call them labels. We can call them names, maybe. It could be different things. And so a label is a datum, right? It's like just a bit of information. And in this particular approach, we are populating nodes and edges equally, right? So you have an edge, which is a bag and spine, with a populated bit of data, which will be treated as a label in our presentation. And so effectively, what edges become are new nodes, because they become new addresses of memory. So you can think of it as this sort of edge place construction visually, where when you have an edge, there's a new node that is just that edge. That's kind of the idea of what nodes are, but we're not going to take that too far, in the sense that we're not going to think about this sort of meta hypergraphs that are built on edges of edges of edges, although there's nothing stopping us from doing it, and it should be quite easy. But just for clarity, we're going to stay at this level. Okay, any question up to here? Because this is basically the definition of hypergraphs. But obviously, until we put it in practice, everyone should be okay, because these are just proposed names, basically. There's nothing.
Is there anything important about labeling that needs to be axiomatic? Like, are there any new axioms we need to add in order to create labels from possibly like thin air?
So labels, I'm leaving a little bit vague at the moment. So if you want some, the mathematical description could be, you would have a map from a set of finite collection of labels, maybe not even finite, but some set of labels into the elements of your hypergraph. The elements being the memory slots, which are the nodes and the edges, right? So formally, it's very flexible. There's no real complication here, and most importantly, there are no limitations. So when I say a map, I mean, some people might say, "Oh, that sounds technical." Whatever. What a map means is really any assignment, right? Okay. So it's completely arbitrary. So you could label everything the same. Like you could have a list of zeros, and everything is okay with that. So that's the point of labels, that they can be degenerate, right? Because they are the bits of information. They are exactly the bits of information that you want to. These are going to be your symbols, right?
Yeah.
In your language, the hypergraph itself is going to generalize data structures, but data structures are sort of the scaffolding around the actual information.
Okay, right? So it's up to you how you want to apply it.
Yeah.
I was just thinking. The reason I'm asking is I might be jumping the gun as well, but it might be relevant in terms of how you apply the labels, because that's kind of like how you identify the data structure compared to the mapping or whatever. And later, like for example, where you have maybe multi-way situations where you just assume that similar identities are the same thing again or different things, it might be relevant. In other words, like where we have like causal graphs that end up like reuniting in the end, we assume that if it's the same, the exact same hypergraph, then you just recombine them at the end, but they could be separate. Maybe I'm jumping ahead to multi-way systems, which aren't here yet.
We can really. This is your intuition should be as basic as when you think of place character displays, or switch arrays in chips and things like that, right? Like, I mean, it really is. I mean, you can think of binary labels, in which case some people would like to call it unlabeled, right? Because if it's just 0 and 1, you can imagine that you have a complete such hypergraph and it's all zeros and some ones, and that's it, right? But anyway, it really is very flexible, and that's the point. But hopefully we'll be able to see that. So, okay, let me flesh out a little bit more why this business of the spinal graph. Why do we need this? Why a graph? How is this going to work? So the idea is that our target is to try and generalize hyperedge symmetry, or at least account for a diversity of symmetries. So you if you follow our streams, or you've thought about hypergraphs a little, you know that there's several kinds of hypergraph that people work with in the literature. There's the very common and basic undirected hypergraphs, which are just sets of nodes. There are ordered hypergraphs, which are the ones that are used in the physics project, for example. So if you go to the physics project website and all the universe sort of generations, they're all of that kind. It's very common in the literature to have directed hypergraphs in applications, in dynamical systems, in complexity science, and so on, which are basically many to many. And obviously, these are important because, as you can imagine, a lot of modern programming languages are built with this sort of infrastructure, although it might not be made explicit. This is sort of the infrastructure that is at the sort of infrastructure level or scaffolding level. You've seen all this sort of like functional programming with all the boxes and the wires and so on. That's effectively what this directed hyperedges are. Right? And then you can have other things like cyclic, where it's kind of in between unordered and ordered, in the sense that there is an internal relational sense of dependence between the nodes, but there's no notion of who comes first, right? So there's a notion that one or A comes before C, and B comes before A, and B comes before C, but there's no sense in which A is first or C is last, right? So it's a data structure that is sort of fundamentally sensical, right? It doesn't have to be justified with other sort of other structures. So And of course, there's the need to do composite data structures where you're not just saying all the elements are symmetrically involved in the relation, but there is some asymmetry. I mean, already directed edges are of that kind, but you can have something that's weird, like you say something, this edge goes to that edge, but then there's a general dependence that goes to the third edge or something, right? So these are things that are in principle possible to think about. In the sense that you want, say, a pair that goes to an order pair that goes to an element, right? So something that has like two inputs, one output. So, but the inputs need to be ordered in some sense. So this is a kind of like a tuple going into an element. So you want this kind of goes. So the idea of a spinal graph is basically to represent the minimal or appropriate graph encoding of the data structure. So perhaps the obvious one is the ordered case, in which you simply say, well, what is my first vertex or my first node? I'll just place it at the beginning of a path graph, so-called path graph, right? This is just chain of directed edges. And then I will just follow along the tuple, whatever the tuple specifies, whatever the order specifies. In something like cyclic, it's also very intuitive that you would write a cycle of directed edges. And it's also very clear that in the undirected case, you should have all possible permutations. So you can exchange all vertices with all of them. So you would have a complete directed graph on the set of nodes. Now the intermediate things are a little bit more contentious. So for example, if I'm thinking of a directed edge here as 3 nodes in any particular order into 2 nodes in any particular order, what I would like to do is to express the fact that there are 3 nodes that are in any particular order. So I'm going to put 3 nodes with the complete sub-directed graph on those, right? The complete directed graph on those 3. And I'm going to look at the complete directed graph on the target nodes. And then in between those, I'm just going to blanket directed edges between all of them. So the way that you should look at this graph is basically, there's no way to distinguish that this node over here is more of a target or more of an output of this node or that node, because it is connected to all of them, and all of them have they are all connected symmetrically, right? So this particular directed graph basically merges all 3 input nodes, the 3 on the left, and give you 2 output nodes. So here's just a sketch. I'm not saying anything very formal. What I'm saying is that there seems to be sufficient expressive power of directed graphs on these things to encode this sort of data structures, right? That's the point here. And of course, the composite here is more motivated left to right. Sorry, right to left in this diagram instead of left to right like the others, where if I happen to draw that diagram, which is as you can see, a non-cyclic diagram, right, a non-cyclic directed graph, then the implication of the kind of data structure that you have is actually similar to what you had here, right? I mean, it is not quite the same because you don't have a complete graph between these 2 input, quote unquote, input nodes, but you do have a sort of a complete bipartite directed graph, unidirectional directed graph to the other. So there is a good sense in which you could claim that the 2 inputs on the left, 2 nodes on the left are inputs, and the node on the right is an output. But then you need this is implying to you that the 2 outputs matter in the order in which they come, right? Because there's no complete graph there. Okay, so I'm going to give some very specific points about this, but are there any conceptual questions here? I mean, just maybe before I say anything else, this is some more sort of in the packet right now. This would be okay. Yeah, I guess I should call it bag. All these things because it's just updated name. So this is kind of how it could look like, right? I mean, this is just a bag of nodes. This is the bag with the spine, which has this directed graph, and this maybe is a cycle. So it's the bag with the spine. This would be an undirected edge that has the complete spine, right? So anyway, questions, comments, criticisms at this point.
Nick, from your side first.
No.
I mean, I like it.
Like to hear that.
Yeah. Well, I like
would-
this. I like this thinking. It feels like you're creating kind of like again like a constructionist type way of getting to these hypergraph edges. I think maybe just to help disambiguate maybe somebody that's newer to hyper edges and this concept of directed graphs in general. What you have on the right looks like directed graphs, but fundamentally it's just a representation of a different, more fundamental concept that could construct the thing that we call directed graphs and all that kind of thing. Or how do you?
Right. So that's actually a super good question here, just for conceptual clarity. So this is mostly geared towards implementation at the moment. So something that can be computationally implemented and mathematically defined, both, to be honest. So there's the sense, in a way, you would have a definition of what a directed graph is in terms of hypergraphs of this nature, right? By having a specification of labels, a specification of data on these kinds of things. But note how I am separating labels. I'm not considering labels sort of an optional sort of decoration thing that you can optionally do on top of your edges, but labels are fundamentally the data that go on your data structures, right? The bags, spines, and that make edges on nodes, those are the infrastructure of the data structure. Those are sort of the scaffolding of the data structure, right? So, I mean, it does have that property of sort of kind of self-referential that, okay, actually, these are directed graphs. Why not marginal hypergraphable? I mean, Stephen made the same point, and it's perfectly fair. There's no conflict there. There's no real problem. It's just that in terms of the concept here is that the nodes form bags which can be spined and can be given some internal sequential or semi-sequential structure, partially sequential structure, and then on top of that, you can populate with information, with data, with actual symbols that will allow you to compute. And I mean, the spoiler here is that we are actually trying to generalize sequential language on computers, right? Like we're trying to generalize sort of place symbol kind of notation in computers. We're trying to make it this graphic notation or this graphic computing language in a sense. So, yeah. So just to comment briefly on that, I mean, this is just summary, so that, you know, if there are some more mathematically inclined people, I mean, as we know, there are in our community. So for those of you who are more mathematically inclined, here's a sort of a connection to some buzzwords that you might be interested in. This is how I'm thinking that that you should mathematically think of these constructions more formally. Like if I see this spinal graph, I'm going to go now in the other direction. Instead of being inspired by a data structure, I'm going to just be given a spinal graph. I'm going to try to give it a sort of a charitable mathematical interpretation and see what comes up. So if I get this directed graph, there's just a path graph with two edges, then the information that is clearly being told, in my opinion, is that you have this vertex is singled out as the initial vertex, this vertex singled out as the first intermediate, and this one is singled out as the last. Those are things, those statements are well defined just in terms of the topology of the directed graph. So that is indeed the information of a tuple, in mathematics. And if you think of it as a set, as we said, you know, bags are sets of nodes, then what you have is a total order on this set, right? You have the notion that you know, it's a well-ordered set. That's what you have. And you know, if you want to think about it as some kind of quiver that could generate something like a category, and you know, you want to start to think about the compositionality of paths in it and so on, then what you're getting is something like a pre-category or a quasi-category. And you know, but we don't have to go too much into that direction for now. Similarly with cyclic, so if you give me a cycle of edges like this, it's pretty obvious that what you're giving me is something that does distinguish the fact that, you know, one or A, B, C, you know, A comes first, then B, that comes first, then C, that comes first, then A, that comes first, then B, and so on. So that internal relation can be mathematically expressed with the fact that there is a group action, right? So you can act with a reversible action here, that is the set 3 action. And it's really just one set three action. It's important to remember it's a group action and not an actual group, because the group would have just the abstract permutations. And this particular graph doesn't have all the abstract permutations, because you can only rotate in one direction, right? So you don't have two group. I mean, if I just give you a triangle of nodes that are connected in an undirected graph, so to speak, I can, and I tell you that you can only flow on paths on the graph, then there are two set three actions, right? Because then you can rotate them to the right and you can rotate to the left. But because this is a cycle, this is an actual data structure, rigid, it has only one group action. So as a mathematical object, that's actually convenient, because that is specifying one single groupoid, if people care about this kind of terminology. So this, you can think of it as the fundamental groupoid, or the path groupoid that gets reduced by some homotopy relation, so that you don't have to count the number of times you are sort of winding the cycle. But the idea is clear. The idea is that there is a notion of symmetry in which a sort of abstract symmetry object, a group in this case, acts on a set of structures, and it gives you a well-defined symmetry in the sense that when you apply the transformation, you get back the same data structure as before. So that's generally a groupoid. You have a set with a group action. The abstraction of that is a groupoid. So that's the idea. Of course, a bag. If you give me this particular graph with all the directed edges, then this should be thought of as a bag, because there's you can put all the nodes in every other which way. So in this case, it's actually, funnily enough, if you look at it from the point of view of symmetry, and this is something that Nick and I encountered many times, is that, and the reason why, as I learned earlier today, speaking with Stephen, the reason why ordered hypergraphs were chosen for the physics project is that you have a lot more ambiguity, even though bags are somehow more primitive or more simple intuitively. If you want to study them sequentially, they have a lot more symmetry, right? They have a lot more internal ambiguity. So if each of these elements has a unique ID, then there are many ways, and you represent them in a tuple, as you do usually in computers, right? In an ordered list, then you're going to have to say, well, if you actually have a tuple there, then you need to have an S3 action on that thing. So you have the action of S3 means the group of three element permutations, right? So you were going to permute that, and you will only see the permutations as a set of transformations on a tuple, right? You need to define a tuple in order to have permutations. There's no sense in which you can have a permutation in a set, because the set doesn't have internal structure.
Interesting. Okay.
So that's why this is why I'm insisting that a group does not encode the symmetry, but a group action does in the case of symmetrical behavior. So the way you get that from from the directed graph, the spinal graph, is by, in this case, again, generating the path groupoid and maybe doing the fundamental groupoid or something like that under some homotopy, where you essentially compose all the possible paths. And then, of course, you get the S3 group, right? I mean, you can go around once, which is a generator of the set 3, and then you can go around a single edge and come back to the same one. And that's the generator of the set 2 subgroup. And those two interact in exactly the way you want. And so you have the S3 group action in there. So you can, as you can see, that you can see this, you can recover the mathematical notions of hyperedge symmetry and so on in different ways. But the idea here is that the spinal graph doesn't care about all that stuff. I mean, that's more like a user level inquiry, right? That you say, hey, I'm going to put this unique address names for the nodes. I'm going to put them in some kind of tuple structure, because my algorithm cares for lists, and my computer is good at doing things with lists. Then from the information of the directed graph, you should be able to generate all the permutations that tell you what are the ambiguities in which you can encode your undirected edge as a tuple, for example. Right, but the beautiful idea, in my opinion, and why I thought this was a cool idea, and why I think there's potential here, and why Stephen is also sort of sold on it, is that the directed graph is a much smaller object. Right, the set of permutations here has 6 elements for 3 elements, but this is going to increase with n factorial. Right, simply the number of permutations. The specification of the permutation is also going to be quite big, because it's going to specify what goes where, right? So it's going to be a lot of data that is going to be put into just encoding the fact that there's ambiguity between nodes. So this is kind of a very sublimed or a very reduced version of having permutation information on the edge, because it's just a graph that is simple, directed, connected. That's it. So it has that sort of property that I mean, this is something that we have to formalize and make sure that we are actually recovering all the stuff we want to recover. But all the examples that are obvious are clear, and many others that are sort of like composite, like the one here on the screen. So imagine that you have something like this, right? That you have a graph that two nodes are in a sort of reversible loop, and so they have two directed edges like that, and you have other one of them that is connected only in one direction. So the idea of this data structure is what we call generally a mix, but the concept is that you have a tuple where the first element of the tuple is a bag of two elements, and the second element of the tuple is just an element, right? So in the same way that you can do tuples of tuples, and you can generate these sort of larger tuples in this way, you can do tuples of bags, of cycles, and so on. And in terms of the directed graph language, there's no limitation. You don't have to care about any sort of rules for how to form expressions or anything like that. You just consider a directed graph that is connected and simple, and you're good to go. And so what's very crucial here, sorry, just to finish this, James, in this final example. So what's very crucial here is that you don't get, so you have a group action on this set, but you don't have a group as a whole, right? It's not like your nodes form a group or anything like that. You have a group action in that you can act with set 2 in the first two nodes, in the leftmost nodes, but you don't have any group action on the other. However, you do have a notion of maybe you call it a quasi-groupoid or something, or like a quasi-category where, I can define paths on this little directed graph, and I can go from node A over here, down here to this one on the corner, and then back to A, or I can flow to C, so to speak, right? And this is compositional. This is algebraic in some sense. It contains internal structure that can be analyzed, but it just does not show up as a group because it is not reversible. It doesn't even show up as a groupoid because in a groupoid, you don't have totality, but you do have invertibility. So it shows up as some kind of composable set of paths, right? And so if you're really obsessed with having a mathematical object that captures this sort of generalized sense of symmetry, then what you really need to have is this sort of a partial set to action that is, kind of a pre-category or quasi-category with this composition of paths and so on. So we don't really need to care about, in my opinion, at this stage, we don't really need to care about what mathematically those things are and how to specify them exactly, because that is in some sense well-known, directed, the paths on directed graph kind of machinery. There's no need to spend too much time there. Here, the idea is much more to think that a spine defines a data structure, and that's kind of the point of the story. Yeah, James, you had some question.
So we said it needs to be connected. In the last composite data structure, that's like this mixed tuple. Then if in a hypergraph rewriting formula, wouldn't this identify a one edge and one disconnected node? Or should we leave the way we write the formulas for hypergraph rewriting as a separate concern to
I haven't really specified anything about rewriting yet. Okay. That's going to be its own thing, right? I guess this was just recapping sort of mathematical recasting of the previous things, so I'll just move on. One first technical point. There's essentially a choice here. Here's where we get into the meat of the question, more technically. So imagine that we were to recover this particular hypergraph that was specifically taken from the physics project documentation. And we are just given this information, right? It's a list of lists, right? Kind of hypergraph. I say, okay, here we have the idea that these things are repeated, right? So we have a 1, and there's a 1 over here. So if we were to attempt to express this as loopless in the sense that we like to think of this as names of our nodes, because that's what they are, right? Like they are the data elements. And the actual nodes are the blank spaces, so to speak, in here. So position 1 in this list, position 2 in this list, position 3 in this list, position 1 on this list, position 2 in this list, and so on. But those are the nodes, the actual sort of bare bones nodes. Then we are met with a problem, or with an ambiguity, right? Because if I give unique if I want to encode this as my nodes and not the labels on nodes, as our Packlet currently does, that has labels as a sort of a decoration on top, then I am met with ambiguity here, because I will give this vertex 1, I will give it a new unique name. So if this goes up to 5, I will give you the name 6. But then there's a question here, okay, because 1 appears in some other edge, right? So should I call it 1? Or should I call it 6, right? I don't know, because, I mean, I don't have enough information to know what I should call it, right? However, if the idea is that these things need to be labeled, right? So I specify for each of the node positions, and so these are and now these numbers really identify the unique IDs of the nodes, and the labels specify the data that is placed on those nodes. Then it is clear that whatever label goes on 6 also goes on 1 and also goes on 6 here, right? So the moment that you actually render the hypergraphs, oops, why? I did not run this before, sorry. It's so sad. In a second. So the idea is that once you label, you should be able to get the same hypergraph from with that has the unique vertex IDs as specified nodes, but nonetheless has the correct labeling, has the correct names. Okay. So I have to do the usual dance of running twice. Yeah, so I ran a very long computation before, and I think so. Yeah, there you go. So, so these are the two hypergraphs. So you can see these are the same hypergraph, right? Like it is they are not only isomorphic in terms of mathematical hypergraphs, but they are sort of isomorphic on labels as well, right? And so what's important here, the point here I'm trying to make is that your node ID encoding is different in those two. I mean, it's an obvious point. This is not deep what I'm saying at all. I mean, these are the same hypergraphs by hand, because I decided to label exactly in this way, right? So this is one point that you don't need repeated node IDs. You can do it with labels. That's kind of the slogan here. It's just a trivial fact. There's nothing clever. But a bit deeper statement in terms of nodes and node IDs and so on is that, okay, important fact, node IDs and node names are not equivalent, right? And that's or names or default labels,
yeah,
and whatever. And this inequivalence really shows once you want to think about loop edges or labeled loopless edges, right? So if I were to render with our current Packlet this particular edge 2 to 1, right, it will render like this, right? And that's fine. It's just graphics. There's no information there. But the point is that so if I wanted to, the alternative, of course, is to say, okay, I can render 1, 2, 3 because it's RET3. It's 3 vertices. But then the labels are going to be 1 and 2 and 2. So there it is. That's another edge. So why one would say in general, whether you want to consider repeated node names or not, or node IDs or not, is just application dependent. So it's not like one is wrong and the other is right. But if you're really believing in this sort of like conceptual picture where we're thinking of the bags and the spines that form the edges as the scaffolding and the labels as the data populate the scaffolding of your and make your data structures, then I would say there's a clear favorite of having loopless edges. And the reason is that otherwise spinal graphs don't make sense, right? Because if I want to give the spinal graph of, for example, this undirected edge here, right? This is 1, 2 to 1 undirected. Imagine, right? I just want to give you a bag of 2 copies of the same object and another object, right? Then I would have to, the procedure will be you have the complete directed symbol graph on that set of nodes. So this is the graph, right? It's a graph between 2 nodes, obviously. But if you do the same thing for this one, then you should see this graph. And so what is, in my opinion, much more important here is that, technically, actually, just to make it more proper. So I think it's, yeah. Oops, what?
Well, remove the automatic.
Oh, yeah, it was automatic there. Yeah, that's right. So yeah, so you can see that in the fact that there is a bag of 3 elements, this is true in both representations in here. Like if you're given a list of elements like this, you're gonna have a bag of 2 elements and then a 3rd element. And here you're gonna have a bag of 3 elements. This is going to be true in both cases. So that means that the data structure of a list needs to be explicitly recovered, right? So a list of 2 elements and a list of 3 elements are very different data structures, right? Really inequivalent, non-isomorphic, different lengths, all the stuff. So I think to me, this kind of settles this is the deal breaker here, that if we are really going to take spinal graphs seriously, then it makes, I mean, it's not only that I think it makes general sense to be loopless labeled instead of multi, but in this case, it makes it even more clear because you won't be able to, I mean, if you just look at spinal graphs, which, as you can imagine, a hypergraph can be thought of as a collection of labeled spinal graphs where the bags are implied just by the labels, right? Then in that encoding, it will be impossible to tell that this is a ternary edge, right? Because it just involves 2 vertices. So anyway, that's
so is that a ternary edge in the first one? Yeah,
no, this is just the graph. This is just the spinal graph that you could write.
Okay.
If you were to encode a ternary edge in this particular way, but which is kind of what these graphics do in some sense, right? Like there's just filling in the space between these edges here. But the point is more conceptual. The point is, if you are representing a data structure that has 3 entries in it, right? So it has 3 memory positions and they are being populated, then the spinal graph that effectively instantiates that data structure needs to be a 3-node spinal graph. It's like saying, what if I just, to me, it's like analogous to trying to say, well, I could always write this as, why not be redundant? I just read this as, 2 sub 2, how can I, index groups? Yeah. How do you do subindex quickly? Oops.
Control minus.
Control minus? Oops.
No,
Control underscore?
minus. It's like control minus. Right?
There you go. Sorry, yes. Yeah, it's like saying, you can save space by doing this, right? And you can say there's 2 2s here and just put it, it's okay, fine, but it's kind of breaking the data structure homogeneity, and it's departing from recovering what is called combinatorial species, which do have this notion that given a combinatorial species, you can, regardless of the internal structure of the combinatorial species, you can always project down to a number, to an integer that tells you the arity. of the thing.
Can,
So if
can
I
I-
were to do,
Sorry to interrupt. You were mid sentence. For my own understanding, can I draw this here and see if I'm getting this right? So is what you're saying is like wait, no, I did this wrong. Okay, it doesn't matter. That's just going to be a loose Hyperedge. Is that it was like one of these. So this is the
what am I looking at?
so this is a Hyperedge, but it is touching that node twice. Yeah. So in other words, that this is.
Oh yeah. Sorry, yes. I see what you mean. Yes. Yeah. Let me make a picture of that myself. So if you have something like a node here and a node here, right? And this is 1, this is 2. This is like if I try to draw a triangle and I collapse the two labeled nodes here, I just sort of like smoothly deform, so you get some kind of shape like this, right?
Yeah, it's one of these creatures. Yeah.
Right. So the idea is that we don't want that. It's almost like you can get this if you kind of like see it in 3D and you go in perspective, and the pair of two labeled nodes are sort of on top of each other, and you don't really, you can tell the vertical, but like the actual data structure needs to keep track. But I mean, this is all philosophy. I mean, I don't want to get caught up in this because this feels cosmetic. It feels like we're just talking about what it looks like and what it feels like or whatever. But that's not the point at all. So
let me clear this quickly. Yeah, I'll do it. There you go. Oh no, I pushed the wrong thing.
Yeah.
Got it.
But these things are actually relevant when it comes to implementing some important.
So there's different visualizations, but when it comes to implementation, we need to do something that can be computed on a computer. So that's why this is important. Yeah.
Exactly. So it's not about how you render it. That's exactly the point I'm trying to make. It's not about how you render it. It's about the fact that do you want always vertex labels to be something that is data on top. So if you have unique non-repeated node IDs, then the node IDs can be the labels. But in general, you're going to have to specify label names so that you can recover all general data structures that you're interested in, right? Which is exactly what, I mean, I feel like I don't really need to defend this because it's like, that's exactly how it works already with most symbolic data structures that computers manipulate these days, right? It's just extending, the paradigm here really is just extending the sort of linear or sequential nature of this list-like notations into a graphic space, to 2 dimensions with this combinatorial.
I just think for people that haven't been exposed a lot to this, it does require a bit of comprehension. So that's why I'm trying to go slow. But what you're saying, once you get it, it makes perfect sense. Like it's very elegant. Yeah.
It is a simple idea. It's nothing sophisticated. Okay, so the whole problem here is canonicalization. So here's my proposal, mostly to Nick particularly, but obviously everyone feel free to chip in. Okay, so the point of canonicalization is that you want to have a procedure that deterministically gives you, so an algorithm that deterministically produces a hypergraph that is isomorphic according to our notion of isomorphism, which, by the way, is an isomorphism at the level of hypergraph. So at the very bottom of this list of objects, right? So a hypergraph is a specification of data, so it means it has to be labeled. So a hypergraph isomorphism is a labeled hypergraph isomorphism, right? It means that you need to, so in other words, if you have this, so these 2 hypergraphs are isomorphic, right? Because they look very similar, but you can swap things around. But as long as the topology that an X is connected to a T alongside an empty edge and to a Y and W in this other edge. I mean, as long as you keep that topology, that's the isomorphism, right? But you always need some labels. By default, if there's nothing labeled, then you're going to think of the nodes as having unique IDs and the edges having unique IDs. And those are the default labels, right? Okay, so the idea is that you want to produce a canonical hypergraph that sort of captures this. Okay, so here's my proposal. It's very sketchy. It's not ready to implement as an algorithm, but let's see. First thing is that we need to systematically label in some way all the nodes. So my proposal is basically to have a sort of rewriting head kind of idea, where imagine that you begin with a simple graph like this. You have vertex IDs v1, v2, v3. Those are the actual IDs. You have the vertex names, so the actual data on those vertices, A, B, B, just to have some degeneracy. So you can see there's no problem with degeneracy. And then some unique IDs for the edges, or names for the edges, like E2 and E1 and E2. Okay, so the first thing, of course, is that you create the spine of this edge. So actually you keep the information that this is E1 and this is E2 by some kind of labeling or some kind of bookkeeping internally. And then you just randomly choose a vertex of your data structure. I mean, you have a graph, you have a directed graph that is typed, in some sense, like colored. Some edges are different colors, and you just randomly choose one vertex. Okay, what you do there is you say, well, I'm gonna use the name 1 at that point. So I'm going to change whatever label is there is going to be 1. So you keep in memory that that location had a name B before, and then what you do is you within your edge you flow. So you do a spinal flow. So this edge now is the one on the left, E1, and you do a spinal flow. Basically, you just do a one-step flow. You come to the next one, and then you detect that your label here is A, which was different from B. Then you just use the next available standard name, which is 2, right? And then you repeat the process until you've traversed your edge, basically. And so then you're there again, and you say, okay, I can flow with another path now. There's another outgoing edge from that vertex. So now I follow that one. So now I'm on a different edge. So you keep the memory B, and then you flow to the next one. The head is there, and it checks that B equals B. Therefore, the name has to be the same. So you give a standard name 1, and so on, right? So again, this is a sketch. I'm not suggesting there's an algorithm, but the sketch is basically that you use the spinal graph sequential information to kind of have a rewriting head that is going to rewrite node names and potentially vertex edge names, as long as you're sort of just when you finish a complete set of paths within an edge, then maybe just rewrite the name of the edge or something like that. And so that basically gives you a standard labeling of your hypergraph. So that's one use of spinal graphs. The other very important use of spinal graphs is the notion of a transform, what I'm calling this cycle flow transform, which basically amounts to how we're going to detect isomorphism and how we're going to take equivalences between different things. So the idea here is that take this graph, 2 edges, 2 undirected edges here with this labeling ABB, and note that and spot for cycles, right? Spot for where the symmetry can apply, and which is basically find cycles in your spinal graphs. In this case, both spinal graphs are cycles, right? Because they are just looping around both nodes. And so you say, okay, if I look at V1 and V2, that's a cycle. Therefore, I can deform keeping the adjacency information and the label and adjacency information from that vertex to this vertex. So intuitively, all you're doing is actually you can implement this as some graph rewriting, some simple graph rewriting, but conceptually, all you're doing is saying, okay, because I have a reversible path that goes from V1 to V2, or V2 to V1, same thing, right? Then I'm going to take all the data that V2 sees, right? Which is the fact that it is connected to V3 with these 2 directed edges and that it's called B, right? And I'm going to flow that information all the way to V1. And that's why V1 now is connected to V3 via these 2 directed edges. but the flow needs to be cyclic, right? It needs to be sort of conservative. You're not destroying information. So you are flowing the same information from V1 to V2. So it's actually like an exchange of information between V1 and V2, which is exactly what you want when you're doing, it's kind of a generalized permutation. It's a spinal permutation. Maybe that's a good name, who knows? Where you're changing the information that a node carries, which in this case is a label name, and adjacency information. It has some adjacency data of other edges. So that's kind of a generalized notion of permutation, right? So in this particular example, we can do it in two different ways, right? We can do it in this way, in which you end up with this graph, which just looks different, right? I mean, in terms of a hypergraph object in our encoding, this is a different hypergraph, right? Because V1, V2, V3 don't change, because these are our sort of immutable nodes that we can't really, they don't have any internal information, but we're populating them differently. Here, V1 is populated with A, V2 is populated with B, and V2 has a connection, has degree 4, or a degree outgoing 2, incoming 2. Here, V2 has degree 2, and V1 has degree 4, and V2 has label A, and V2 has label B. So this procedure has changed the hypergraph, but what's important is that it has changed it in a way that is completely deterministic. We've only detected a cycle, and we did a flow transformation within that cycle, right? Restricted to the cycle. So the highlight, the blue highlight is the cycle that we're highlighting, right? Is the V1 V2 cycle that you find in your directed graph, and you flow along that particular cycle, and then you get this, and actually you get back to the same thing if you do it again. You can just apply it again, and because it's a cycle, it's going to be reversible. So you're going to cycle for a finite number of times, and then you're going to come back to your original configuration. But you can also do the same thing to another cycle in your graph, which is the V2 V3 cycle. And in this case, well, same story applies, right? The information, the labeled and adjacency information from V2 travels to V3, and the adjacency and label information from V3 travels to V2. So you get this hypergraph here. So the idea is, if you take these two hypergraphs, so these are complete encodings of hypergraphs in our sense. If you take these two, they represent exactly the same hypergraph, right? Because again, remember, we don't really care about the node IDs, because they're just unique and distinct, right? So we obviously call them different in our computer or in our mathematical notation or whatever, but these are the exact same hypergraph, right? So obviously that's something that we have to do computationally. I mean, we have to say that these two are isomorphic. We need to do some kind of directed graph isomorphism between these two to claim that they are the same hypergraph. But the point is that this conceptually, the way I see this is that these two objects here are already encoding, I mean, that and that, they are all encoding the same hypergraph. They don't give you different information in terms of what a hypergraph is more ontologically. But in terms of the computer implementation, these are four different. Well, these two are the same. Sorry, three different. These two are the same, just different highlights. These are three different instantiations of the same hypergraph. And what's important is that they were generated in a deterministic way from the information of the directed graphs, from the spinal graphs themselves. Okay, that's basically the idea. The questions and criticisms and whatnot. Because I am very naive with these things. I'm not a computer scientist. So.
Well, first of all, I'm a bit confused. Aren't spinal graphs are supposed to represent the symmetry of the single hyperedge, not of the hypergraph overall?
Yeah. So that's, maybe I should have highlighted that these are colored in some sense. Like you see that these two directed edges belong to E1, to the edge E1, and these two belong to the edge E2. So you perform these operations on an edge-to-edge basis, right? So this symmetry, I mean, this is the ambiguity in terms of the canonicalization, right? Because you want to use this kind of transformation to eventually define one single hypergraph that is the canonicalization of the hypergraph, right?
Well, you said cycles. You picked the cycle, not the edge. That's what you said, right? Well, what if you have hyperedges connected together, forming a cycle which is not a single.
No. Cycles internal to the edge spine, right? Which is the generalization of permutation of element in the edge, right?
Okay.
So it's only cycles internal to the edge spines, not general cycles in the graph. Yeah. I should have clarified. Yeah, it's only, and I'm saying cycles because it feels like that's the thing that is reversible. But I want to think that maybe there is a bit more general notion where it's actually any kind of flow. But in some sense, if it's not reversible, your labels are going to like disappear because you can't flow in a conservative manner and not destroy things, right? Like it's a bit weird. So in the cyclic case, it's obvious that you have to account for this kind of freedom, because I mean, what this is, another way to put this, I mean, forget about what I said in the last 10 minutes. Another way to put this is that if I give you computationally these two expressions, right, with V1, V2, V3 being my, IDs in my computer, and I give you these exact graphic structures with these exact labelings, they are different in my computer, but they represent the same hypergraph. So this is a notion, implicitly I'm giving you a notion of hypergraph equivalence in computational terms that,
So I have a question. What is the reason for this? Like maybe just if we go up one level, just to come back to the motivation.
Yes. So the reason is that so far I have presented a concept of a hypergraph, right? Mm-hmm. Like I have presented what I think should be a hypergraph in a very general sense, where mm-hmm. edges encode these general symmetry structures with partial symmetry, blah, blah, that stuff that is inspired by this modern notion of combinatorial species, and I think it's very powerful and so on. And the problem we had, I mean, this idea is not new. This is what we thought for a long time, and kind of we all agree that we should be implementing eventually. The only new thing is this idea that spinal graphs are going to be the tool, kind of the infrastructure that is going to allow us to define algorithms to efficiently manipulate these kinds of objects in the same way. Because the analogy is that when you have a least hypergraph or tuple hypergraph, like the ones in the Wolfram Physics project, mm-hmm. or the ones that it has worked with a lot and so on, or the back ones, like people in the Hypergraph X package in Python do, and Nick also did some functions with sets and so on. Like the problem is that those are symmetry specific. They rely on the specific structure of the specific spines of those edges to do the algorithm. So in some sense, this is just a generalization of that. It's not really changing the philosophy. It's more like generalizing the philosophy. So what you do in canonical hypergraph, sorry, in the canonicalization of the physics project hypergraphs, as far as I can see in my head, because this, again, it's a bit vague what I'm saying here, but as far as I can see, it's a generalization of these sort of procedures where you're using some idea of flowing with a head in a data structure, and you're basically just counting positions and so on, and you're equivalencing under some relation. So you have this idea that, I mean, of course, like that if you change the order of two edge expressions in your list of edges, that's going to be the same hypergraph. However, the system is going to see it differently. Right?
Okay.
Yeah.
I think that goes back to what I was trying to say earlier, when like equivalency in the Wolfram Physics project thing. I think I didn't use the right words, but that moment where you try to equivalence things, it gets tricky, because like it depends. Like we're not explicitly rewriting them back to an equivalent hypergraph. So what you're saying here is, regardless of the node IDs that you have to create in order to like hold the information to do the computation, the data that you're trying to represent needs to be somehow equivalenced computationally, and without doing like a massive search or something. This is a algorithmic way to determine equivalent hypergraphs. Is that one way to say it?
Well, that's the goal. I'm not saying this is a procedure yet, because this is just a sketch.
Okay.
Sketch.
Okay. So the reason what we're trying to do here is we're trying to find ways to determine equivalences between the hypergraphs themselves.
Yes, but in a very specific manner, in a very specific sense. The sense of, once the hypergraphs are implemented in a system where, I mean, the hypergraph as a conceptual object, as a conceptual entity, in my opinion, is this kind of drawing where you have topology and you have labels. That's a hypergraph. That to me is a hypergraph, right? Conceptually. But in the same way that you would say that a number, conceptually is just an element of an arithmetic algebra or something, or whatever, your favorite definition of number, or like one of the von Neumann, whatever, right? You pick your favorite formalization. But when you put it into a specific computational framework, you're going to have to express it in some way. So a number is going to be eventually like a symbol in a place, and maybe that symbol corresponds to some accumulator or some kind, it's going to have this sort of like infrastructure to express the arithmetic behavior of that. So my point here is that the infrastructure that you need to express hypergraphs in the conceptual sense that I am proposing, which is basically a crystallization of all the things that have been discussed that are in the zeitgeist, I would say, like from pure mathematics to applied network theory to the physics project to all these things. In my opinion, those concepts require this thing. They require nodes with unique IDs, and they require bags, which are basically declarations of subsets, which is extremely primitive, nothing fancy there. And then the only contribution of mine to this discussion is that instead of our previous suggestion for our previous approach for this, which was how the Packlet, or is how the Packlet handles it, was you declare a list of nodes. So actually, instead of a bag, you have a tuple of nodes first, and then you specify some equivalencing with symmetries. So you specify some permutations, some generator of permutations, and that's how you get equivalent expressions of lists, which are implementation different. They are sort of language level different, but they represent the same conceptual hypergraph, or the same conceptual mathematical, so to speak, edge. So my contribution here, the change, is more than a change, is really a generalization of that. It's saying, instead of baseline assuming that we have a tuple and we have to do play the permutation game, instead assume that you have a bag that clearly delimits your, sort of selects your set of nodes, and construct some graphic structure, directed graphic structure on that effectively is capturing this idea of generalized symmetry. And because it is very clear that there's a one-to-one correspondence with the important structures that we know, tuples and cycles and bags and the ones that we really care about, and is computationally amenable in the sense that you can build algorithms with directed graphs very efficiently, right? I mean, I'm not an expert, but I just know that there's a massive industry that I can go to just optimally do graph isomorphism when necessary. I mean, it's similar to what Nick was doing when the hypergraph isomorphism algorithm that we have right now. Actually, I mean, Nick can speak to it because I don't know the exact details, but the idea is that you transform a hypergraph into a directed graph, and then you do isomorphism of that directed graph, right? Which effectively, I think it was the line, some kind of line graph of the hypergraph, right, Nick?
Well, there are two versions.
Okay.
First, we transform arbitrary hypergraph with arbitrary symmetry for each hyperedge to just a directed hypergraph, ordered hypergraph, right?
Yes.
So we basically duplicate each hyperedge, performing all possible permutations of that hyperedge, right? Given by its symmetry. So now we have a directed hyperedge. Then we can do a usual directed hyperedge canonical transformation, right?
Yeah.
And then we just labels can be canonicalized as a post processing after that, right?
Yeah. So anyway, just as an example of using directed graph algorithms very efficiently, right? And so anyway, this is where we're standing, I think. And I mean, again, as I said, this is a sketch of a sketch. There's no implication of an algorithm here, but we've just to rephrase, and because I can see a couple of new viewers here, the big problem that we've had is that we know if one deals with directed hypergraphs in which edges are just tuples, so order lists of elements, we have very efficient ways to deal with it. That's very well known. We have resources. If you want to deal with undirected hypergraphs, which you're just looking at bags of your nodes, again, That's just basically subset. So it's set theoretically very efficient. Again, easy to do. If you want to mix the two or do any other kind of partial symmetry in your edges, then there's literally out there nothing. People have, as far as we can tell, there's no offer of good ways of dealing with. I mean, if you define a hypergraph as something that can mix those kinds of edges and be part of the same data structure combined, there are no good algorithms on offer to tell you what you should do to deal with those, because you end up with this sort of ambiguities of like, do I include all the permutations of the hypergraphs and so on? And so the interesting idea of these directed graphs is that they can give you a kind of a universal way of just encoding symmetry that is graphic itself. So you can rely on graph algorithms, you can rely on rewriting if necessary, you can rely on kind of the mathematical technology or computational technology that we are already using for these kinds of things. So yeah, it's basically, conceptually, it's like trying to outsource the problem of symmetry that we've called it before, the symmetry problem for hypergraphs. It's kind of to try to outsource it to a graph problem, which...
Can we define symmetry? Maybe yeah, I don't understand symmetry.
Yes, symmetry is... I say symmetry, it should be saying generalized symmetry, because it is symmetry in some cases is explicit. So symmetry in this sense, right? If I give you a tuple, you would say that this is a rigid structure that has no symmetry, in the sense that if I change anything in it, the information changes, right? Mm-hmm. If you imagine like visually moving the things around, or you have a physical object that, actual information of the specified data changes. In a cycle, if I change things in a careful way, meaning I put where A was, I put C, where B was, I put A, and where C was, I put B, then I get a bit of information that is indistinguishable. Mm. So physically, a tuple you could imagine as having like a rod with beads, and like two fixed ends of the rod. So the beads can like shuffle, but they will always have one that is like at the right end and one at the left end, and inside they can move. A cycle would be like the same construction, but you have a circle. You have a metal circle with beads inside. So they can move around, it doesn't matter, but they are in a cyclic structure, right? And then a bag, as the name suggests, is like you take the beads out and you put them into a bag, right? And that's, so, I mean, it sounds very silly, but this is honestly the best way to think about it.
So where's the symmetry in those examples? Saying that the cyclic and the unordered...
Yeah, the symmetry is in the discrete operations that you can perform on your objects, so that you won't change the structure of the object. So in the tuple, anything you do, except the identity, except the do nothing do, which is a bit weird to say, then you get some new information. In a cycle, if you have 3 beads on a metal loop, right, on a looped wire, if I teleport these 3 beads into each other's positions exactly in a cyclic manner, meaning that A goes to B, B goes to C, and C goes to A, then you can play around with it physically. You will get the same object in your hands. It will not change.
So is that a symmetry? Are you saying that that's the definition of a generalized symmetry?
That's the usual. Yeah, that's the usual. That's the usual convention that people. I mean, symmetry conventionally, in sort of more physical or more broader sense, because for mathematicians, symmetry normally means group actions, like very technical. So you have a group action, that means there's a symmetry. Okay. And generalizations thereof, so groupoids and bundles and group bundles and things like that, right? Whatever. But more physically, more intuitively, a symmetry is when you have a sense of reversibility and indistinguishability, right? So if you have an object and I can perform a distinguishable action somehow,
indistinguishable.
I can perform a distinguishable action, but the object that results is indistinguishable. Then you can say that you found a symmetry of your. I mean, this is the usual thing, right? I have a glass here, I'm rotating it. I'm sure that it's very hard to see that it's actually rotating with this resolution, right? So that's because it has a symmetry, right? We say that, and the symmetry is not that this is a group; it's the fact that there is a group action on this object. Right?
And your actions are distinguishable in terms of, they say maybe you're turning it leftwards, you're turning it rightwards. So those are 2 different actions, but the symmetry of the glass never changes. Yeah.
Exactly. No, the symmetry never changes. The perceived glass actually never changes.
Yeah.
If you look at it closely, you can see my fingers rotate if I do it carefully. you basically see my fingers move, but you don't really see the glass move that much, right?
Yeah.
So that's kind of that's the idea of symmetry, right? Like something that is measurable changes and something that is measurable doesn't change. So you say that the thing that the measurable change is acting on with a symmetry transformation, and the thing that you didn't see change, right?
Carlos, here's the question about the spinal graph.
Yeah.
Right. Because the one thing I don't understand, because we have this general notion of symmetry as just a permutation group, right? That can encode arbitrary discrete symmetry.
Yeah.
Which is just a list of cycles, or rather, list of permutations, which on its own is a list of cycles, right? So how do you distinguish? Like, imagine like you have a Hyperedge RT4, right? And you have such symmetry that you can just swap two pairs of vertices, but only together, not independent of each other. You only swap it together. How you can encode it as in the spinal graph?
You can swap it. Why can't you swap it like this?
Yeah. That's a good question. Okay, so it's very good that we think of extreme cases. Let me just draw, see if I can make sense of it. So you're saying that you want. So what is the symmetry you want? You want two edges that are all bound in a bag. So the ones I'm drawing are in the bag, right? In the edge bag, and you want a symmetry in which you can swap these two, the two vertical ones, but not any other way around, right?
No, only vertical, yeah, just
only vertical, right? So then, wouldn't you agree that that means that you have really like a tuple of two things that can be permuted?
Okay.
Right.
Well, maybe there's like a more complicated case.
Because I mean, like it's clear to me that these symmetries will have to be included. I mean, I think we both agree on this, right? But these two are clear, right?
But they have to be together.
They have to be connected. That's the point. So, so I could say maybe actually the way. Yeah, actually, maybe this is the way, right? So I could just draw this, for example. To me, this would be like a tuple of two bags, right? So to me, this looks like I have like a bag of two things and a bag two things in a tuple that's ordered. Maybe I should connect direct here and direct there as well, right? But just to keep it clean, I'll just not draw those, but something like that. But I guess you could also complete this symmetry here. And I mean, I'm just thinking as we go, because I think there's a new language. I don't know exactly what the language is really saying, but there are many options, right? Like this is not the same as completing the graph, that I can actually interchange the corners, because this feels like I can permute like this and I can permute like this, like as a whole.
Yeah.
Right. But I can't do all the permutations, right? Because I cannot permute this. And remember, these have like actual ID, like V1, V2, V3.
Yeah, well, all I'm saying is just like we have a simple symmetry that those pairs of vertices can be swapped simultaneously, and that's the only group operation that you can do. And it's like,
wait. You say that the only operation that you can do is that they can be swapped simultaneously, both of them?
Yeah, it's like this. Well, swap this vertical.
Okay.
Horizontal layer.
Okay. So then you would agree with me. Then it's the complement of this, right? You would agree with me that this looks more like a bag of two tuples, right? In terms of,
yeah,
right? Like you have two things that are rigid that can be permuted, and they can be permuted with each other, right?
Yeah.
So then you just draw the equivalent thing for that, which would be, I think something that I wrote. No. So where's the So I think you erase for example, this one's. I think that's what it would be, for example. And maybe you complete here. I'm not sure. I don't know if you would have to complete. Because as I said, this is a sketch. I haven't really.
Wait, wouldn't it be? So it's a bag, right? So wouldn't it have to be? Wouldn't this still have to be connected here, and then you just have an extra one here?
No. They have to be simple. No.
Oh, okay.
They have to be simple.
Sorry.
So, I mean, you don't want to connect back because then you lose. So, you might in this case actually. No, actually, I think this is right. I think this is you're preserving. You have two tuples, and you're preserving. So what if you made the complicated thing? Is what if you made this into a three tuple, and that complicates it a little bit. If I wanted this to be a three tuple, so I have that, then clearly I would need something that goes here. Right, so I will have a three tuple in here. So people don't get confused. I'm drawing that one. And the question is whether you would also have to connect. Like there's a degree of there's a degree of freedom here. Like, why am I connecting this one to be 3 and not to be 2 to be 1?
Yeah, and it's like your algorithm with the cycle is still, it's like if you pick just a single cycle of V1, V2, right? You can't really look at it alone, right? Independent of other cycles. So kind of.
No, I see what you mean. Yes, I see what you mean.
So it's a correlation with cycles.
Yes.
So
but
that's why I don't understand like how this directed graph can encode this whole symmetry. So it has this ambiguity, what's the direction of those things. Like I understand you can directly encode it as each cycle as a hyperedge, right? So if you encode an arbitrary symmetry of a hyperedge, you just draw a hypergraph on top of those vertices that correspond to all the cycles somehow, right?
Yeah.
Maybe color it so that it's like each permutation element, each element of the permutation group is colored, right? And each cycle is the hyperedge.
Yeah.
That's like direct encoding of the arbitrary permutation group. It's just like a hyperedge. But as a directed graph, the spinal graph, I don't understand how we can do it.
I completely agree. I mean, I'm glad that you asked, because my idea is that the permutations. So let me be very clear. I was just trying to guess for the discussion because I thought it was a good exercise for me to try and get one particular example that you had in mind working. But just to be clear to everyone here, the idea with this stuff is that you generate the symmetry, not that the symmetry is encoded in the directed graph, right? Like you generate from. I mean, this is not the symmetry of the, like these arrows here don't. I mean, in this particular case, I mean, let me give you the quaternary case. Like, this thing explicitly contains all the permutations that are possible, right? Because it's just the complete directed graph. But you would have to, like in practice, you would have to generate what the transformations are. Like in the sense that, if these are, let me just give numbers as IDs, right? If these are numbers, and in your computer you actually put them in a list, 1, 2, 3, 4, right, in some kind of tuple. The directed graph in this particular case actually gives you kind of like choices of flows give you permutations, but a choice of a flow is a very special choice within a directed graph, right? Meaning a flow, meaning that you choose every vertex once and so on, right? So from 1, I'm going to choose a vertex to go to 3, for example. From 3, I'm going to go to 4. From 2, I'm going to go to 1, and so on, right? So it's going to give me But
So you have
clearly,
the path. So
exactly, but
basically-
exactly. So I should have said it more explicitly because I just buried it
So,
in
so,
the. Yeah, go on, Nick. Yeah.
so what is it? A Hamiltonian path through all the vertices,
Yeah.
right?
Exactly.
So all of those.
Something like that. Yes.
Well, maybe in that example, those edges have to be in opposite direction, so you have to go. Otherwise, you can't really make a loop through all the four vertices.
Exactly. Yeah. So the symmetry, the symmetry proper in understood as if I have a list expression for my vertex IDs, how do I encode the ambiguities or the redundancies explicitly? It will have to be generated from the directed graph, from the spinal graph. This was the whole point. It's not a trivial process. It's not directly. It's kind of like generators, right? Like the generators of permutations are not all the permutations that you have. So these are like generalized generators in some sense, and they generate by maybe doing paths up to homotopy or something like that. I don't know. I mean, it's a mystery to me yet. Like I haven't figured out how to do it. But it seems very plausible, and the promise seems like the gain might be big if we actually figure it out.
I'm not sure it seems. You say it's a generalized, so do you think it's even more general than permutation group, or what? What do you mean generalized?
Yeah, it's more general than the permutation group, in my opinion, because it allows for things that are not permutations, right? Like paths on these things are more general than permutations, because like
We'll make one example.
Yeah, can we guys do some examples?
Yeah. But let me clarify my point. So what I mean is that there is no group action in the spinal graph of the ordered one, for example, right? Like there's no.
Well, this group is trivial. Yeah, it's a permutation group is trivial for the ordered one.
There you go. Oh, okay. There's no non-trivial group action. Yeah, that's what I mean. Yeah. But in this, not this one, but the example I had down here, for example, right? Like I have a group action that is local to 1 and 2, and then a trivial action that is only applying to 3, right? So this is like it's a groupoid. It's a bit. I mean, you can encode it as a permutation if you only care about cycles, right? But the whole point is that we might care about information that is more than just cycles, specifically for these kinds of algorithms, right? Specifically because we might want to know efficiently how to navigate the edge in some sense. Like the spine of the edge is kind of the navigational map of the edge. Like that's, I'm using just conceptual words, but like my idea is that it is some kind of navigational map of your edge, because it's the idea that when we're trying to do undirected hypergraphs, like we do kind of canonicalization, you're like, okay, so you're intersecting with 4 nodes, and 4 nodes are intersecting in 2. How do we name them and so on? The problem was that we didn't know how to navigate inside the edges and how the intersections of the 2 interacted, right? That was the problem. So there was some notion of how you go through all the, because you have to check all of them, right? Because we want to be extensive. Computation, you want to be complete. You want to exhaust your objects. So you need this idea of, like, as you say, like Hamiltonian paths or something like that. So it's some path stuff that we have to do within edges.
Well, do you have some motivation for that particular symmetry when you care about just the flow? Right? And all the symmetry you just can, it's the all possible ways you can, permute your vertices. That kind of makes sense. But when you just have this set of vertices, which is and you want to somehow encode the flow from one vertex to another, that's basically what you call generalized symmetry, right?
Yes.
You're not permuting them.
Yes, exactly. Yeah, what I call generalized symmetry is paths in a, let me put it very simply. You know that you can get exactly Z3, the cyclic group, or S3, the permutation group. These groups you can get mathematically exactly from these graphs by doing the homotopy paths, right? Like just define path up to homotopy, where homotopy is just defined that If you can have several composed paths, then you're the same basically. Then you get you have an infinite class of paths because you can be as long as you want, and you quotient by this homotopy relation, and the concatenation of paths is the composition. That becomes your group composition, and that object mathematically becomes isomorphic as a group to set 3 in the case of a cycle, to S3 in the case of this triangle of directed edges. But in general, that same procedure will not yield a group, right? If I don't give you something that has cycles, it will not yield a group as a mathematical object, but it will be nonetheless perfectly well defined. Like you will have a set of paths and homotopy relations between them, and you could compose them locally. Like that, the composition algebraic structure of these things it's perfectly well defined. There's no problem. But you might see just the trivial action. You might just not like, as I say, in a tuple, you see only the trivial action, only the trivial group, like the non-group, basically, like the single element group. But there is a mathematical structure there, which is a total order. It's a very strong mathematical structure that you have in a tuple, right? Which we absolutely exploit computationally. We absolutely use the fact that you go, one after the other, and we do sort of sequential operations on tuples, right, one by one. So my point is that because in the unordered case, I have a lot of symmetry, and we use those as permutation, and we encode them as permutations to do our algorithms. And in the ordered case, we use the rigidity or the lack of symmetry as an asset as well for our algorithms, which is to say that we use the sequentiality of the structure to go one by one and do accumulations and do sequences and so on. My idea with these graphs is that I don't know how exactly. I mean, I don't have the answers for specific examples and so on. But my idea is to try and push and see what is common in both cases, in the cyclic or more symmetric case and the fully rigid tuple case, and try to bring them on the same ground with this notion of a spinal graph. That's kind of the summary of why I'm motivated by doing this. Because it seems to me that...
What about some data structure, which is not just this mix of tuples and bags and cycles? Because those clearly can be represented by permutation group, right? What about...
What's an example?
Can we do like a whiteboard and then just go through different examples one by one? Maybe that'll help. Like, just start with like a very simple case, then add complexity, and go through the whole process of how to get this symmetry.
Sure. Yeah. Let's definitely use a blackboard. But do you have an example in mind, Nick? Where?
Well, I'm asking, for example, when of a data structure when the permutation group is not enough.
So I'm not saying the permutation group is not enough. What I'm saying is that, let me put it this way. Permutation group is relevant when your node list is actually a list, right? When your node IDs are put into a tuple, and they are put into this list tuple thing in your encoding. That's when permutation groups are relevant, because that's how a permutation group is defined, right? Mathematically.
Yeah.
Like, you could think of as well as a map of elements, the unique elements, blah, blah, blah. But, in terms of data structures more directly, more explicitly, you define them once you put them into an array. So my point is that there are no arrays in our data structures, right? The idea is that we really only use bags and graphs, right? So we do away with arrays entirely, in some sense, right? I mean, we might obviously want to use them computationally to the specifics, but the idea is, if you imagine that you don't have arrays at your disposal, then the analog of a permutation group is something that is a bit more general than a permutation group, that becomes a permutation group when you find cycles. But it's more general in the sense that you have paths. I mean, perhaps I'm saying general because to say that when you care about path information on your edge, it's not only about symmetry, right? Symmetry is not the only thing that you care about. You care about navigating, in some sense, like navigating your edge computationally, like to perform some like canonical labeling or whatever, like these kinds of things, right? So my point of these directed graphs is that they're going to be generators of path algebras, call them as you will, right? They're going to be generators of some path information, some path compositional structure that
Well, maybe we just shouldn't call it symmetry to not confuse people.
I completely agree. I gave a disclaimer at the very beginning. I said, I'm going to say symmetry, but I really mean this sense of generalized symmetry that's not really symmetry. It is, I would call it just edge type. Like, like I wouldn't say, like, symmetry is just a property of edge types. And some of them happen to be very symmetrical, and some others happen to be not symmetrical or partially symmetrical, right? Like if you have a many-to-many map, like back-to-back, like this one here, right? I mean, there is, in some sense, a lot of symmetry, but in some sense, not symmetry, right? If you just obscure the bags, there's no symmetry. If you just look at the bags, there's full symmetry, right? So, yeah, let me join with the Blackboard and.
Yeah, I need to see some.
Edge type. So it's essentially the edge type is supposed to encode all possible paths through the vertices of the hyperedge, through the generators, but it doesn't have to, like, naively you can just express it as all possible paths between those edges, or between the vertices in the hyperedge.
Yeah, exactly. So if you have the spinal graph, you will be able to generate such set, but you don't have to encode. You don't have to keep it in memory. That's the point.
And the paths are through all the vertices, right? Not just like partially.
Exactly.
Maybe.
Generally, they are through all the vertices. Yes, exactly.
What about partial then? Is it more general?
I mean, no, the paths are partial. No, the paths are not through all the edges. That's, I mean,
vertices. Well,
through all the vertices. Sorry, yes, no. So, I mean, not necessarily, right? I mean, maybe that's a good definition. Who knows? Like, I don't know. Like, I'm sure that complete paths or whatever, Hamiltonian paths or some version of these, I'm sure they're going to play an important role in like algorithms and designing like a specific thing. I'm sure. But the idea more abstractly than when trying to communicate here is that you have the spinal graph, and naturally in a canonical way, in a mathematical sense, canonical, in a natural way, you generate this path information that basically you have a map of how to traverse this. And there will be, in an order edge here, you are told that you can go back. There's no path that goes back from this to that. It's just no path.
Well, it's clear to me that it's some kind of separate edge type. It's not clear for me now that you can also simulate the symmetry as a permutation group with this particular type. Maybe they're completely separate. They have some intersection, but the symmetry, if you trying to express this edge type with the all possible paths through the vertices of the hyperedge, I don't think it can express arbitrary symmetry in terms of permutations and cycles of those vertices.
Not, of course, not with the paths period. You might have to do something like homotopy equivalence or some kind of equivalencing of paths, or look at only cycles, and like cyclic paths or something like that, like to bring out the permutation expression of the symmetry or the permutation expression of the type. Like the type is going to have a natural, like you say, okay, I choose an arbitrary sequencing of my nodes, my node IDs, then my claim is that any DAG is going to have, any spinal graph is going to have a permutation group assigned to it, 100%. Like it's clear that that's the case. But to me, that's just one expression of the path information of that spine, right? I mean, it's not the only information that I can get out of it, in the sense that, again, if you give me a set and you tell me it's a tuple and you say you have no symmetry, you just have the trivial, you only see the trivial group, that's no information. That's literally like 0 bits of information, because there's the identity map that I already had on a set. But if you tell me there is a total order on this set, that's a lot more information than just tell me you have a set and no group action, right? So that's what I'm trying to capture here, that even in the case where there's no permutation allowed, so only the identity, even in that case, I still have an internal structure that tells me that 1 comes before 2, comes before 3, comes before 4, and so on, right? So that's what this is trying to So, I mean, again, as I said, sketch of a sketch, and I apologize. This is the early stages of ideas, and we're kind of theory crafting here to a degree, but let me see if I can join. So James, what kind of example?
Like the most basic one, and then also, and then we go from there, because I like this thing with the reading head that can like go to different, that can like follow the spinal flow.
Yeah.
I just wanted to see that in like a few different examples, basically, and then see what the end result looks like.
Yeah, I'm not sure I'm gonna have the ability to show. Let me see. In the sense that the head idea is precisely what motivates me to think about paths in the first place. So what do you think about this, Nick? Actually, I mean, forget for a second about the subtleties or details of the permutation and so on. But don't you agree, like morally speaking, that if we're interested in an algorithm that is going to canonicalize by doing this kind of thing, that you go like node by node, changing things and keeping some memory of what you've seen and so on, that morally speaking, what you want is information about how to traverse and like how to flow in your somehow. But do you see the relevance?
Intuitively, yeah. It's like if you interpret your spines as some kind of paths, that's what you're supposed to do in order to define this, right?
Yes, exactly.
Yeah.
No, and that's exactly what motivates. I mean, if anyone is wondering why the hell did you even think about spines like this, like directed graphs in the first place, is because I wanted to think of paths inside of an edge. I wanted to know what is the connectivity structure of the nodes inside of an edge, and I realized that permutation groups were. I mean, permutation groups. Let me put it this way: permutation groups are perfectly okay. Like they do fine, but the problem is that for computation, they are very big, right? They have a lot of information. They blow up super fast. So I should have maybe prefaced this. I didn't say this. Like one of the big motivations to try and find an alternative encoding of symmetry or this sense of generalized symmetry is precisely that you don't want, if you go to order 4 or 5 or 6, the size of the data that you have to carry is huge. If you're carrying the actual representation, the equivalent representations of your edges, and just the number of pattern matching cases that you have to check and everything, it becomes huge, right? So, I mean, just as an anecdote that many people might remember, that I made this comment last week during the workshop. The guys at the Hypergraph X package in Python could only do motif detection up to RT4. And when I asked why, they said, well, because above that, it was just intractable. It was too big. It's like too long to compute, too inefficient. So, I mean, and that's crazy. I mean, I had a conversation with Nikolay during lunch, so offline, and he was saying, with all my respects, and I like these people, I'm friends with them and so on, but this is really not good enough. Like we can't stop at 4 and say, for domestic computers, 5 RT is already too much, and we can do pattern matching with 5 RT, right? Which is what they were claiming with their methods. So this is a big motivator. So I should have maybe prefaced by saying that I don't think there's anything wrong with if you want to encode your hypergraphs as tuples, as lists of IDs, of node IDs, and you have this symmetry encoded as permutations. That's a complete description, as far as I can tell. Yeah, as far as I can tell, that really gives you a complete description, right? Because tuple is the most ordered thing, and you're gonna have, as far as I can see, that's the best. That's a complete description. I mean, I put an asterisk in this claim because it might be that some data structures that are more partial are only expressible with graphs, but generally speaking, I don't see a limit. I don't see a limitation really with that. But the motivation was that we needed an encoding that was much more computationally efficient and amenable to algorithms that were already sort of out of the box, which we didn't have at all for mixed symmetry. I mean, that was the big problem, right? I mean, that's what Nick and I had discussed for some time, like months now, not continuously, but over and over again, we find like ourselves saying, "Oh, how do we deal with when an edge has this symmetry type and these other symmetry type? How should they interact when there's adjacency between them, right? There's some incident structure between them. It's not obvious at all how you deal with like canonicalizing those kinds of situations. So the spinal graph idea just appeared as a possibility of just trying to use out of the box technology, so to speak, which is directed graph stuff, which is probably the most streamlined stuff that we're going to find for anything graphical out there, and just try to basically don't invent it, right? Like we just adapt directed graphs to what we want to express in terms of edge symmetry or edge type, and then we follow the standards, take the polished machines from the industry of graph algorithms, and just apply them in our setting. And so, because our algorithms are going to care about hypergraphic level stuff, and this is just edge level stuff mostly, right? And how edges interact when you care about an encoding that needs to be sequentialized. Because again, and let me bring it to a very basic level. If we had computers that actually spoke hypergraph language in some sense, right, where you could actually encode this kind of thing primitively, right, and just deal with it, then we wouldn't be thinking about this, because we'll just work with those things and we'll just compute with those things and that's it. But the matter of fact, we don't have those, and we have a language like Mathematica where we're working with that requires lists of lists and things like that to encode hypergraphs. But because it already has very efficient encoding of graphs, my thought was, okay, maybe graphs is a good way to, it's a new angle of attack, because we're stuck. I don't think we had a real, at least I didn't have any good ideas on just using permutations in a very general sense. It looked very complicated.
While we're on this page, can I quickly ask a question? So are we saying that this is the hypergraph data of the hypergraph that is this guy again?
Yeah.
Yeah, okay.
No, wait, not this one, sorry, no. This is just a pairwise graph. So this is just this would be the kind of diagram that you draw, like in category theory, where you duplicate an object and you say, A, B morphism, but because I always have identity, I can duplicate A, so I copy A and I draw some identity arrow between A and A. And in some sense, you have added nothing to the diagram, but or just imagine that whatever. There's a molecule that just, it's some chemical species that has that sort of, I don't think there's any chemical that looks like that, because it just makes no sense. Because if B has, but if I just rewrite, right, and I just write BBA, then it's like water, for example, right? It will be a graphic model of a water molecule, just by changing A for B here, right? So it's it's a primitive object. That's why I'm sharing here. So let me share. Yeah.
That spinal graph does have an equivalent hypergraph representation, right?
What do you mean?
So if you can go from any hypergraph to a spinal graph, then can you go from any spinal graph to a hypergraph?
If the spinal graph is labeled correctly, yes.
Depends on the labeling. Okay.
No, I don't mean that it depends on the labeling. What I mean is that just a directed graph will be one single edge, right? If all the information you have is like directed graph structure, simple connected directed graph, unlabeled directed graph on a set of nodes, that would be a edge information. So if you have a general directed graph, simple directed, I mean, not even simple, to be honest. In fact, should not be simple, because otherwise you're not going to express everything you want. Any general directed graph can be made into a hypergraph as long as you pick your subsets, your subgraphs, and you label them accordingly, right? So this, I mean, let me draw here. I have my whiteboard here. So in this particular case, this thing can be turned into, it's doing the 10-second crash every time, as usual. So this particular graph can turn, sorry, what was I going to say?
One edge.
Oh, yeah. Sorry, yes. So this becomes same thing. Wow, so much lag.
Do you want to do the Zoom whiteboard? We won't be able to use your pen then. Oh, and you've got the images here already.
Yeah. So you would get a symmetry thing here, and you would get a symmetry thing here, right? So, and of course you keep the labels if you want. That's secondary to this argument. But yeah. So that directed graph, if you keep track of the coloring or the labeling, then you uniquely recover that hypergraph. That's kind of the argument.
Wait, which hypergraph? This
one.
Okay.
I mean, when I say hypergraph, I mean any graph, any hypergraph, all graphs are hypergraphs.
Wait, but don't the labels have to be unique?
No.
Oh.
No, a hypergraph, I mean, it's good to remember. A hypergraph is a data structure where you have a bag plus spine construction on each set of nodes, and then you assign to each memory place a data value, which is a label, that counts for nodes and edges if you want.
A bag plus a spine.
It's a bag plus a spline. This is what I'm just going to update it here. An edge is a bag plus a spine. It's exactly this concept.
Okay, I thought that the bags give you spines. That's maybe where I was missing it. So what you're saying is these are different things, and you can create combinations of these things.
No. So bags are always the same. Bags are just sets.
Yeah.
A bag is fully characterized. I mean, the only way to distinguish bags, other than by the specific IDs of the elements, is by their size. It's the only information they carry, just size, cardinality, which some people might call parity of the edge in the end. But spine can potentially, and this is what Nick and I are debating, and we will have to figure it out. But spines can encode much more information than that. That's the idea. That they can give you a range of types, and that's the whole point. Some of them very much like stating symmetry roles about the edges, about the nodes involved in the edge. Other things giving you like a hierarchy. For example, trees. You have a tree type in this, right? Where your directed graph looks like a tree, right? So that I should have maybe included this example more explicitly, right? Like multi-rooted trees kind of thing, like where you have like actual DAGs, there's a whole class of edges that have DAGs as spines, right? Directed acyclic graphs as spines. So, by the way, those are the kinds of things that you want when you want to use these hypergraphs as diagrams for things like functions or mathematically what people call operas, where you want to write this, you use trees usually for expressions, right? For composition of expressions and for nesting of functions. So you want edges that have exactly that internal structure, and that look like I have a maybe 3 inputs and 1 output, right? And this is directed. And, in this case, we might not specify symmetries between them. And then that might be a different kind of statement than actually saying full symmetry between them, which is a kind of a funny thing, right? Because this is saying that, like, if I specify this edge type as a quaternary edge, or this edge type, where I draw, where I draw this kind of thing, but then I actually assume the full symmetry of the thing at the top, right? These two things are different, but they might look intuitively similar, right? Because the one at the top, both have this clear sense of input-output, 3 inputs, 1 output, but the one at the top and the one at the bottom says that there is full symmetry between the 3 vertices, but the one at the top just says no information about transpositions of the input nodes, right? So I'm not really sure what this means, or what this should mean. But to me, it seems that it has expressive power, right? It has some kind of, because I can also have another situation where, I have the same sort of idea, 3 nodes that are input, 1 node that is output. And then instead of having the full symmetry between them, I have a tuple kind of symmetry, or tuple kind of structure. And you have this, where this is your edge. So there's a sense of a list mapping to a single map, and that's the more common. I would say that this would be sort of like a 3-hairy function. The other 2 would be like, this would be a symmetric 3-hairy function. And this is, I don't know, but it looks kind of like a symmetric 3-hairy action. But in a computational sense, I don't know what you make of this, but in a computational sense, to me, maybe I'm crazy, but to me, it seems different to have no information about permutations or to have the information that all permutations are allowed, right? So to me, the first case, the question mark case, is no information about permutations. No information about internal structure, internal ordering structure of my objects. The one at the bottom is a tuple internal structure. The one in the middle is full symmetry internal structure. These to me seem computationally distinct to me. Intuitively, the one that has full symmetry and the one that has no information seems similar, because like you think of graph isomorphism and you think of being able to move things around because it's isomorphic. But that actually depends on you interpreting that as a graph in a mathematical sense, and not so much about what your data structure means. But yeah. Anyway, the point of today was mostly to present the idea and to make sense of the concept of spines, sort of more conceptually.
Do you think like this idea of spines, is it even correct to call it a hypergraph if you want this kind of type of edges? You can as well call it that you have a directed edge now, directed graph now, but you just have some edge covering that you call hyperedges instead.
Sure. Yeah, that's informationally equivalent, in my opinion. But the point is that you technically recover what people call hypergraphs, right? Like, I'm not denying that's a feature, not a bug, in a sense, right?
Yeah.
Like, again, because I think it's good to be able to express hypergraphs as directed graphs. I mean, there's a level of the hypergraph or the directed graph that is not a directed graph, which is the label, which is very elementary, which is just subsets of nodes. But I mean, the more I think about it, the more I am convinced that a hypergraph is essentially that, right? A hypergraph is an information about collections of arbitrary size that have some internal structure, and the internal structure is, I think, is more general than a directed graph, than a spine in this sense. It could be other stuff, more general or whatever, right? But if we are interested in applying algorithms that go and cover all the nodes because we want to make sure about things and rewrite and do all these kinds of things and use efficient isomorphism checks and things like that, using directed graphs seems to me like a, I don't know, like a no-brainer choice in some sense. Like, not least of which the rewriting rules. I mean, many of these things can be implemented via rewriting rules. Like, you can define many of these operations that I was referring to, like these things. These are actual rewriting rules. Like, I could have written them with our Packlet even right now, and so you could define equivalents of graphs as like this idea of belonging to the same state space, right? So you might like actually implement things in the language with these explicit graphs, right? Where you say, okay, these are the graphs, these are the transformations that apply, and this is what an equivalence transformation is, which means this is a confluent rewrite system, and they will give you a set of not confluent, a terminating rewrite system, and you look at all the normal forms. That's all your equivalent representations of a graph, kind of thing, right? Yeah, I feel like I've been converted into graphic thinking, and like now I just want to make things out of rewriting and try to exploit as much as we can existing graph technology, like actual pairwise graph technology, because yeah, anything that is more hypergraph specific, the actual difficulty of hypergraph stuff comes when it has to do with the ambiguity of how you sequentialize things. And I can say that from many different angles. I can say it from the more computation and sort of implementation angle. I can say it from the mathematical angle, that when people study hypermatrix algebras, for example, there's a huge amount of ambiguity of how you order your indices, and indices changing some positions actually dramatically affect the algebraic properties and so on. Like, and this is all because it's not obvious what the internal hierarchy of sequence is for nodes. So having this requires a little bit of theory, I think. I mean, it just requires a little bit of, explicitly working through. I mean, for next time, obviously, I'm gonna try and cover examples of things that are not obvious, and what might be the difference between having full symmetry between all of them, or just symmetry between sort of cycles and so on. But yeah, that's the gist of it.
We need to write code for this now.
Say it again, James?
We're going to need to write code for this somehow eventually.
To what? Sorry.
We have to write code for this somehow.
Oh, right. Code, yeah, for sure, absolutely. Yeah. That's the entire point. And here the implication being that it might be that we only need the existing code, the existing functionality for graph processing in the language. That we don't have to invent. We have to use it in a specific sense, but we just have to, when we do canonicalization, we basically go edge by edge, sort of like. So Nick, actually, this comes back to all the way back to the idea that I had that you can sort of do canonicalization by somehow doing hypergraph paths, right? Where you go like one edge, then you find an incident edge, and then you canonicalize first edge, and then based on that canonicalization locally, that sort of spills over to the next one, and so you keep going in that way. So that's why I wanted to have DAX to navigate your hypergraph. Because that's essentially the two things that you do in the canonicalization process, right? Like you look at the names in each edge, and then you arrange the edges themselves, right?
Yeah. Good. And I'm not sure what do you mean. Canonicalization just you order your edges in some particular way and rename your vertices.
That's what I meant. Yeah, that's exactly what I said. Yeah. So in this case, if you imagine that your hypergraph is not, let me put it this way. So when you compare hypergraphs for isomorphism, so that you do this canonicalization, the way I guess it works in the implementation right now is that you canonicalize both and you check if they are equal, right? For isomorphism, right? Yeah. So my thought was that if you have, so in some sense it's some kind of alternative approach that's inspired by the same idea, but alternative in the sense that if you have a way to give, so the first thing, this first row here of process is how you give some standard naming to all the nodes, right? And so that, a hypergraph, two hypergraphs of the same number of nodes, they're going to have the same names, right? Okay, but that's not very difficult. It's just some systematic way to do that. So you keep all the information faithful, whatever. Then the difference in approach here is that if you define a set of transformations based on spinal graph flows or whatever, symmetries or whatever, like we have to understand. But imagine that we have understood that and we have a way to say, okay, these are the allowed transformations that you can rearrange your adjacency data and your label data so as not to actually change the hypergraph data proper, the hypergraph object proper on that graphic expression. And so that's a set of rewrite rules, and you have an initial graph that is canonically labeled. So you just run the multi-way system, you get all the terminal states, and then so that's your isomorphism set, basically. You just check equality within that set, right? That will be another strategy for isomorphism, right? You agree?
Yeah, just not sure what it's. It's not even clear why you can just canonicalize the spine graph itself. Because you're still going to maintain the information about the hyperedges. We just what we already do while converting hypergraph to a graph. And then
maybe that's just completely trivial, and I was just trying to.
I think it's just equivalent, yes.
Yeah. That seems completely right. As long as your directed graph equivalence keeps track of labels and these sort of colorings, like edge labels.
You know the mapping, right? You always know where your edges map to. So you
Yeah,
can
yeah,
recover the hyperedges, covering each, like before and after you do the canonicalization of the spinal.
yeah, for sure. Definitely. Yeah.
But is the problem then the combinatorial explosion of the higher arities if you just do it that way, Nick?
Perhaps, basically, if you have a large bag hyperedge, it essentially requires to turn it into a complete graph, right? The spine going to have a complete graph, so many edges.
Yeah. But
But you don't need to permute every single version in order to find a symmetry. Is that what you're trying to solve for here, Cross? Is you're trying to figure out a way to say there's like a formulaic approach to prove symmetry or show symmetry that doesn't require you to permute every possible directed edge version of a
Yeah.
hypergraph?
basically, I mean, what Nick just said, that's right. That's what I was looking for. And what Nick just said, I don't know why maybe I was too tunnel visioned into this rewriting idea, but if you somehow do a canonical labeling, because you agree that you still have to do some systematic labeling first, right? And but that seems easy to me. I don't know, just systematically keeping track that things are tidy.
Well, I don't know. Like, for me, labeling is not even important at all. As soon as you canonicalize the topology of the connections, the labels kind of can be canonicalized afterwards, whatever, however we want.
But how do you
Sure.
check in the case where Carlos had 2, where the 6 and the 1 could have been flipped and that ended up with the exact same information? How would you be able to check for that case?
That's my point. That the labels might be non-unique. They're not like IDs, right?
Then yes.
I mean, as long, I guess your point. I think I get your point. As long as your canonicalization procedure, which is really just a colored graph, labeled colored graph, right? Canonicalization. As long as that respects the labels, then it should be quite easy. Once the topology matches, then checking the labeling is easier, right?
Yeah.
So yeah, so maybe it's my claim is stronger than what I was saying. Maybe my claim is precisely that if you have this encoding with spinal graphs, as long as you keep track of the names, colorings of the directed edges that correspond to hyperedges, maybe I mean maybe not. It does reduce to just canonicalizing the directed graphs, as long as those things are kept. And we make sure that there's no destruction of information. So that's exactly what I had in mind. Like that is a solved problem. Canonicalizing a directed graph. That's and I'm sure we have powerful algorithms to do it. Right?
It's just maybe the whole difference that we did to what we did previously. It's like when the conversion to hypergraph, right? Or to graph. Because when we canonicalized directed graph before, we turned like every hyperedge into a new vertex. So that's how we made a directed graph out of hypergraph that we then canonicalize. In this case, you already start, you have the same set of vertices, is not changed. And
Yes.
it's not clear from you how those correspond to each other for some reason.
Oh yeah, no, it's not
Maybe
clear.
it's not enough to, I don't know. For some reason, it seems to me that it's not going to be enough to canonicalize spinal graph. Although I'm not sure.
Yeah, no, I get your point. I mean, I also had the intuition that it was not enough. That's why I didn't think of it in the first place.
Well, maybe it's like it's just a little procedure is different. Maybe it's even more efficient. It just requires this post processing, which pretty trivial to just canonicalize the order of your edges, of your hyperedges that cover the spinal graph. So after you canonicalize the directed graph, you also canonicalize the ordering of the hyperedges that cover it. So like this two procedures together.
Yeah.
to canonicalize it how we did previously, like introduce a new vertex, then get rid of it again.
Yes.
Yeah.
Yes.
So-
Because basically that new vertex is essentially accounting for the order of the hyperedges, right? Like the ordering of the hyperedges is essentially introducing these new vertices, right?
Yeah.
In the way we did it before.
Well, we did it like maybe pretty trivially because we have the symmetry is encoded by just introducing new hyperedges, and then all those hyperedges introduce a new vertex, so it's kind of very explosive.
Yes. So yeah, but that I think that's basically the idea. And yeah, I was just thinking.
No, I keep coming back to trying to understand the importance here of equivalency. I still don't think I fully grasped why that is important as a problem to be solved for where we're trying to go. Like, why do we need to equivalence?
So the main reason, I have two answers to that. I mean, maybe Nick, you want to go first if you have an answer. I'm actually curious to hear what you say before I do.
No, I don't.
Okay.
Okay. Your two answers. Yeah.
Okay. So my first answer is what I had written here on the screen, that what we want to represent with a hypergraph conceptually, like number 2 in your screen, like a set of pixels or an ASCII code or whatever it is, like what we want to represent with it is not exactly what we are encoding in the language. If I imagine how this would be encoded in the language, it's not exactly that, because for example, the unique IDs of the nodes, which will be the node names in Mathematica, right, in the language, those my arguments today have been to try to argue that we don't really need those at all. Like we need to use them to compute, but we don't want them informationally, so to speak. Like conceptually, they don't carry information, right? So what carries information in a hypergraph is the topology and the labels, right? And how it's like topology structure and how you sprinkle that topology. And so because we don't have computers that speak natively that language, it's just a matter of fact, right? We don't have computers that have that sort of embedded in their architecture and their natural like programming languages for that and so on. We're trying to build one such thing, right, on top of Wolfram language.
Can you explain topology? So you said it's topology, and what was the other thing?
The sprinkling of data on it, right? Like assigning data to the nodes.
And the labels.
So the labels is data, right? That's data.
Labels and the labels of the edges and the vertices.
Yeah, both. Yeah.
And the topology is the relationships.
The topology is the relations between them, right? We're saying topology in a loose sense, and we're saying topology as in like what is the connectivity structure between.
So it's almost like you have a unique ID in order to identify all the nodes, which is just a remnant of having to be able to do these things computationally. Then you have data at every one of those IDs, which is like a string or something, and those could be the same or not the same. And then you have relationships between those things. So for me, that's like just an SQL database. Again, I don't know why I keep having that analogy in my head, but it's...
Yeah, but that, I mean, a database is one specific kind of such data structure, but we want to be more flexible than just that kind of database. Because that database, as far as I understand, is kind of a table structure, right?
Sorry, let me not jump into maybe not good analogies for what we're trying to identify right here. So the point is that you have labels and relationships, and now the reason why we want to find equivalences is what?
That the way we are expressing relationships between labels is non-unique.
Okay, but why do we want that? Like,
No, I mean, it's on the screen, right? So if you look at the screen, like on the screen, you can see that these two things,
they should be equivalent, but on the computer, they're currently not. So you'd have to search somehow. So maybe the bigger motivation here is like, there is this maths that we're trying to develop. There's like this formalizational kind of process that's hypergraph rewriting, or just like the world of hypergraphs. The problem is that when you try to do certain types of mathematics with these hypergraphs on a computer, they're going to give you results that are difficult to achieve, that you could just draw on a blackboard and see that it's like obvious. It's like obvious that those two things are the same looking at it, but when you try to compute it on a computer for higher arities, it becomes almost impossible.
Yeah. I mean,
Okay.
I
So
wouldn't like that final phrase might be a bit too much, but like
it
in a sense
becomes
that-
increasingly difficult. Yeah.
Yeah, but the spirit is right. I think the spirit is right, and I really think this is very analogous to what happens with, how you code arithmetic if you only have, say, like accumulator variables or something.
Yeah.
Right. You like with a usual even the constructivist mathematical definition of arithmetic. Like if you only have a successor function in set theory, that's enough to construct arithmetic.
Oh,
right.
Maybe.
But you don't have like ab initio. You don't have arithmetic built in. You have to define some relations, what things mean the same in this way, and then you sort of arithmetic pops up. Right. So this is the same idea.
So maybe the question is like, in order to do mathematics in order to do the maths of hypergraphs on a computer, we need to somehow have a very efficient way to say that this blue version at the top and the orange version at the bottom are equal. So we're trying to create the algorithm for equality that's efficient.
Absolutely correct. That's exactly the point. I don't know if Nick
is equality a unary, like what is equality is it a function? Like it's a binary
relation.
Okay.
An equivalence relation mathematically. But Nick, do you agree that that's a strong motivation to have such a notion of canonicalization?
Even motivation just to be able to do it fast and efficient.
Or to do it at all in a reasonably efficient way.
Yeah.
Sure.
So you're saying at the moment you can do it, but the way you're currently doing it is you're permuting every version of how you could express it on the computer, and then you're comparing each one. Nick, is that how you can?
Yeah.
Not really.
I mean, there's the problems, right? We can do it for tuple hypergraphs and for undirected hypergraphs. We have functions for those.
Okay.
But the undirected hypergraphs is slow, and it's expected to be slow because of the combinatorial explosion. But also, we don't have a way to generally treat types of edges that are not undirected or directed.
And
that's the bigger price.
So the mixed case, we currently have no way to do it.
No. I mean, there's a way, which is just to separate the hypergraphs, because you can always grade by type, and then you canonicalize independently, and then you put them together again. But so there's a way to do mixed as in order and unordered simultaneously. But yeah, it's not. I mean, the technique is, as far as I understand, the technique is not even amenable to one and the other. They are like different algorithms based on different ideas, aren't they?
Well, they all circle around the idea, just convert everything to a graph when it's already solved.
Oh yeah, exactly. Yeah. So my thing is just another flavor of that.
Yeah,
spinal graphs are just another flavor of that.
But a graph has ambiguous ways to be represented in memory. That's the issue, right?
No, but the thing is, that's already done at the language, right? Like all the functionality for graphs is already encoded at the language, like labeled graphs or whatever, or like we can. The point is, my suggestion here is because Mathematica has very efficient and extensive functionality for graphs specifically, right? And so we can use it to our advantage and, for example, define vertex names in a systematic way so that they are actually representing of IDs, of unique IDs, and use our labels in a way, like, or encode the labels in the vertex names if necessary. Like we can be more hacky, once we are already using graph functionality, I would say, and not only like built-in functions or built-in symbols in the language, but we can use graph algorithms like that are out there, like with some repository functions or some functions that we code ourselves with sort of cutting-edge graph technology that people are. I mean, this is an ongoing field of research, right? I mean, it's not like graph analysis is just done and finished, but there is a lot of technology there. I mean, if you compare to hypergraphs, like you go out there, and we invited the world experts last week in Paris. Like last week in our hypermatrix workshop, we had a good representation of the world accumulated knowledge on hypergraph software in some sense, hypergraph computation, and these people were clueless how to do this. So are we, but we are trying to find ways to be better at it.
Okay, another question here. So just the pure mathematics doesn't necessarily have the labels or the data you're applying to the hypergraphs. That's the part that seems a little bit disconnected from the pure mathematics of what you can do with hypergraphs. Like this is kind of like we're trying to place data on top of the hypergraph and then kind of like do hypergraphic things and then see what happens to the data. So that disconnect, I think, is what's causing a lot of the problem here.
Yeah, I mean, you can call it problem. You can also call it fun in some sense. In the way that, my point is mathematical hypergraphs are super boring, in my opinion, because they are either just literal collections of relations on a set or literal subsets of the power set of a set. Right? If you go to the mathematical literature, that is 99% of what hypergraphs are for people. The other 1% actually do directed hypergraph, which is many to many, so tuples to tuples. So it's just like putting arrows between tuples in some sense, right? So in my opinion, those are very boring in the sense that what people have done with them is very boring. It's not that the objects themselves are boring, they're just objects. But what people have done with them is, in my opinion, quite boring, which is they systematically just do combinatorics, which is glorified counting. And all my respect to combinatorics, it's a very difficult field. I am very inexperienced in it, but it has a purpose, and the purpose is to count, essentially. And they count in extremely clever ways and extremely interesting ways, but the purpose is to count stuff. So my purpose is that I have zero interest in counting, and like maybe sometimes I would like to enumerate something, but I have zero interest in what properties of counting there are in these things. I mean, that would be interesting if we want to make something efficient or something like that, but the goal here is much more different. The goal here is really to kind of the dream is, in some sense, is like we want to extend computational language from string-like, tree expression-like to graphics, to like graphic-like expressions, right? Which is, in some sense, is like upgrading from the natural sequence, right? Like you go from string to tree, then hypergraph, right? To me, it's just the natural sequence of generalizations, right? And we're not generalizing for the sake of generalizing. We're not like just trying to see, oh yeah, we do this because we can, and then we see if it's useful. We have very pressing questions in like infrageometry, the physics project, the hierarchy, this abstract categories. Just before this meeting, I had a meeting with a collaborator of mine that is also attending the workshop virtually, and they were thinking, how do you encode these abstract NRE categories where you only specify a rewrite system and so on? Like we don't have, I mean, the best tools we have at our disposal are rewriting systems for those things, because we know that algebraically they don't have axioms, and we have to treat them computationally, sort of infra-mathematically than mathematically. And so we are trying to build a language that is capable of doing that. And so a lot of this effort with all this spinal business and all this kind of nonsense is that we know what hypergraphs we want to account for, right? Like we know that we want tuples, we know that we want directed, we know that we want cyclic, we know that we want undirected. These things are things that we definitely want. But we want to also be able to exploit graph algorithms and all the stack of graph knowledge that we have, and both implemented in the language and as sort of out of the box results from the literature. And so if you put those things together, that's how you come up with spinal graphs. I mean, in this sense. So yeah, I don't know. I don't have a much better way to sell it, but in the last few months of development or thinking about it, this has been the first time that I see like a different approach that has a kind of obvious way to do canonicalization, where you actually canonicalize these typed or colored directed graphs, and which, as Nick mentioned, really is very much within the philosophy or the sort of the ethos that we were already doing, which is you turn your hypergraph into a directed graph, and then you use directed graph isomorphism to check for pattern matching. And because obviously, I mean, this is important for pattern matching. Like, I mean, I haven't talked about rewriting at all today, but this whole problem of I mean, we're constantly talking about isomorphism and equivalence, right? The main use of this is pattern matching, right? You want to know when two edges match in a pattern, and so this is exactly what you needed.
Yeah, so hypergraph rewriting, your rule has to find the pattern somewhere. So if there's an efficient way to do that, that's very important. Yeah,
absolutely. Yeah.
So isn't this a kind of a normalization problem, like data normalization in a way?
I don't know what that means. Maybe Nick knows the term. Data normalization.
Like I'm thinking, yeah.
Which one?
No, like I'm thinking basically what you have here is you have a structure where you've got a many-to-many relationship, which is a problem in most relational databases because you have to have an association table. So you have to create a new structure in order for there to exist a many-to-many relationship. And where you're trying to say that the data that any one of your entries is similar to another piece of data, you could have this association pointing to the same thing, but they're two different associations. So it's denormalization. So what you need to do is you need to squish those two things down. So instead of having two associations, you have one association that points to the same data. It was the same data anyway the whole time. The point is they had different paths to get there. So that's called normalizing your database. Is you're trying to avoid duplicate data in a way. It might be too of an abstract thing to think about. Too
abstract of an analogy, but yeah,
it's a big issue because there's other ways you can structure data that you actually denormalize, and that's efficient for different types of things. And then so there's different ways you can think about the data. I mean, I'm just taking a different field that kind of feels like it has a similar problem, but it's just there might be some ways to think about how they've resolved it. Maybe I'll look at that a little bit in my spare time as well.
Yeah, could be. I mean, hypergraphs, I mean, relational databases can be expressed in terms of hypergraphs, of course.
Yeah.
Hypergraphs are really, they're meant to be this very all-encompassing data structures, right? I mean, just to rewind everyone to square one or chapter one of our spiel here, and how why we are branding ourselves with hypergraphs, why we care about them at all, is that they have extreme flexibility for data structure expression, and obviously it's not so extreme when you only thing that you can do is tuple or bag, right? Like that's not a lot of expressive power. It is, you need these intermediate structures where, to be honest, I mean, I'm just excited about the prospect of maybe even having this cyclic structure. These are not common, right? Like you don't typically, like bags, you have an intuition for sets, and there's a lot of algorithms that use sets, and tuples or lists is much more common in computation. But having things like cycles those look like kind of hyperdimensional Rubik's cubes in a sense, right? Like where everything is cyclic, but everything is interlocked, right? So you've seen this sort of like Borromean rings, like expression of Rubik's cube. I don't know if you've seen that animation before. Oh wow, they even sell it. Let me bring it to the screen and share. You see this? So see, there's like this structure that is, those things are cycles, right? Like they are, the beads inside are in a data structure that has no first, has no last, but they are clearly ordered, right? They only have the ambiguity of back and forth, but once you go in one direction, they are well ordered. So
that's pretty cool. I've never seen this before.
Yeah. I mean, if you see, there's an animation of Rubik's cube.
Wonder what the world record solution for that is.
Oh, there it is. This thing.
Oh yes.
It is an animation.
Okay, okay. Very cool.
Yeah. So the things on each loop, in each circle, they are in a cycle data structure purely, and then these cycles are in a hypergraph effectively. This is kind of an example of a cyclic hypergraph in some sense, right?
That final one was really cool, where after they've solved it and they spin it around, that's kind of what you're trying to say. Those things that then become equivalent, because it doesn't matter how you spin it.
Yeah, exactly. So yeah, it's interesting. I don't know. I feel it's a very cool concept, and if we can develop like the actual computational stack to deal with these objects. I mean, the good thing is that we are going to be pretty, I don't know, far ahead of the competition in some sense. And if this is a stable thing that does all the things that hypergraphs are supposed to do, so they can encode higher order networks and do network analysis, network science kind of stuff more generally, I think it's a very cool, so it's a cool thing to do, right? Like we are breaking ground in some sense. Like we are at the forefront of what computational languages are like, and so solving this problem needs creativity and needs some kind of inventiveness, because people haven't tried to solve it that much, because nobody really had the need for general hypergraph language. But it is increasingly, like Francesco Lotito that talked in the second day, the final talk of the second day. He's the developer in Hypergraph X, and he said that he's looking at mixed hypergraphs or directed. Directed hypergraph means many to many. So this sort of like many to many structures. But he said that he's struggling with it, and it's like, I don't know how I should be doing this, and so
this is a serious computer. This is a serious like problem in computation. It's a serious problem. Yeah.
Yeah, it's a serious problem.
Computer science problem. Yeah.
Yeah, and I mean, there's a component of mathematics, there's a component of language design, there's a component of just algorithm design. So it has a bit of everything for everyone to like in some sense. So for our audience as well, if you have any ideas and you want to participate in the process of the development of the hypergraph language, then come to our community. Very welcome.
Isn't this basically a search problem?
Which one?
Trying to find the equivalence between the data of what two hypergraphs with different IDs for the nodes, like where they are equivalent.
I don't know, search problem maybe is not very well defined.
Yeah.
What do you mean search problem?
So you're trying to search for where the data of the hypergraphs are identical, even though the memory addresses are going to be different. It's like this specific combination of addresses that give you this data should be identical to a different set of memory addresses that give you the same data.
Yeah, but the challenge is that you only have access to the same data, like the same data structures on your computer, right? So you are the one declaring that these two are to be equivalent.
You're
That
checking.
needs to be operationalized, right? So in some sense, the computer doesn't know what equivalence means, but you know, and you tell the computer, do this process. When this process happens, I'm going to interpret that these were equivalent, but the computer will never know that they are equivalent in some sense, right? That's the challenge. I don't know. Do you agree, Nick? Is that a good characterization? How do you think of it?
Maybe. What you do is essentially the canonicalization part, right? So
Exactly. So canonicalization means that you express your objects as a same kind of object, but in a standardized way, sort of an orderly way that then you can equate, not equivalence, but actually equate. And yeah, so
Feels
it is
like-
a search problem you're there. Yeah.
It almost feels like maybe it's a different analogy you can use. It's like when you draw an actual hypergraph, sometimes like on a 2D plane, it's going to be on a Euclidean space that has maybe an X and Y coordinates. So what you're trying to do is say, ignore the coordinates and try to identify that these two hypergraphs that you drew in a space are the same, even though the lengths are different and the things may be in the different way around. It's like you can't help but physically, when you draw in hypergraphs, they have to be in some Euclidean space. So what you're saying is, how do you say that these things are equal, even though the shapes are different and they're in different locations in this space?
Yeah, that's an analogy, yes, because computationally we don't really need to care about that.
Yeah, we don't care about that, yeah. In fact, you have to ignore it. No.
Yeah. I mean, it's not even there. Like that information is not even there, right? So, I mean, I guess when you render it, it's there in the language because it's an actual graphics object, whatever. But yeah, we don't even keep track of geometric information in our encoding. So it's much more about the discrete data structures. But the analogy is correct. Like that's exactly correct. Like you have many isomorphic manifolds.
So maybe this canonicalization process basically, it's almost, I keep thinking of maybe it's like a hash map or something, but you basically have this canonicalization process that gives you a canonical word or string for a specific hypergraph. And then if you canonicalize another one, it gives you the identical string and you just compare those strings.
Yeah, that's basically what we do, right? I mean, it's just that the question is how you construct such word.
Yeah.
Okay. That's what we've been discussing. Yeah, but that's essentially what we do. Because I mean, you can take the expression in the language as the word, right? Like the actual expression of the end process of the canonicalization as the word.
So how you equate them, there's different algorithms. I think that maybe that's what you're trying to say. So I need to sometimes reword it to figure out exactly what you said 5 times already. But it's like there's many ways you can equate two long strings. There's like multiple like algorithmic optimizations to figure that part out. What you're saying is, how do you get from your hypergraphs that are inherently embedded in some kind of memory space to canonicalize it, discard all the other information so that you can get to a place where you can compare the raw information to each other? Like how do you describe a hypergraph canonically so that there is only one string representation for it and then compare the strings?
Yeah, I mean, that what you said is correct, but you don't need to say that you have to discard anything, because the problem we are posing here is
sure, that doesn't matter. Yeah, those relationships can exist. The point is like, maybe this is like a simple way to describe it. If there was hypothetically a way to have an ID for every possible hypergraph, then this problem would be solved. You could just compare the IDs.
I mean, an ID, you mean for the...
Like an identification. Like you can say like, okay, ID A is just like a node. ID B is like 2 nodes and a single edge. ID C is like 3 nodes with 1 edge in between them. And then you can basically you can permute every possible combinatorial possibility for every hypergraph. Like, in other words, you could create a map of every single hypergraph if you had infinite memory, let's say, and then you can just compare the ID of this graph to another graph.
Yeah, I mean, you don't even need infinite memory. I mean, if everything is finite, that's not the problem. But I think that
how do you extract the ID? How do you extract the ID given the hypergraph?
Exactly, like that description misses the problem here, which is that you have a substrate that computes in a certain way, and you know that you have the ability to uniquely identify certain structures, and you know how to transform between them, but you're still unsure how to systematically always transform in a way that you keep the equivalence that you want to keep. So it is very much the sort of user level demand, right? Like you want your system to do something for you, and this thing that we're trying to do is part of the discussion today. I want to make sure, also as a form of wrap up, because it's been almost 3 hours now. I'm trying to do 2 things with this sort of more conceptual presentations and these discussions. I want to, on the one hand, like Nick and I did for a little bit, like and yourself, James, to ideate a little bit what it means to do this spinal stuff and how to try and imagine sort of sketches of algorithms and so on for canonicalization and whatnot. But on the other hand, and this will be even more apparent when we talk about rewriting next time. What I want is that we all agree on what it means conceptually to do hypergraph processing, right? Like this, because that's the most important thing. Because if we don't know and this was the problem, that the physics project just rushed to something that was operational, because this is Steven's style, and he's welcome to be that way. But we need to be extremely decisive with what it means to do hypergraph processing in conceptually before it gets any digit of code is written, right? Like we need to be extremely precise with that, and that's what Nicholas Baer was complaining about. I mean, in conversations to me, he was saying many people that are working in implementations that use some kind of graph rewriting languages or graph grammars and things like that, their problem is that they are not precise enough what the data structures are and how they are transformed, right? So we have we need to do our due diligence. We need to be very, very precise what we mean by those, and that's why I said, conceptually these are unique ID nodes that are sort of like unique but indistinguishable and featureless, and then on top of them we build the bags, which are just sets of those, and then spines, which are just directed graphs on those, and then these things are at every step. Everything is perfectly well defined. There's a well-defined mathematical theory for them. There's a very standard computational treatment for those objects. And so, when we get all the way to rewriting and actual, definitions of what it means to be confluence systems of hypergraphs and so on, we will be able to say to what degree does the categorical rewriting stuff apply to our stuff and so on. Like that would be a good test that we did our due diligence. Not so much because we might think that it's super important to use categorical rewriting and rule algebras and all these things that Nicholas Baer was talking about, but because I think if we can do that more or less easily, it means that we did our due diligence correctly and we are in firm ground to build, right? So that's the main point. And so yeah,
it's a big problem in potentially in machine learning as well at the moment, is merging matrices or computational graphs. It's a big optimization. If you can solve for a way to define explicitly how to merge any 2 computational graphs, that'll be that'll be very important. We had one comment here from Brady. So he said, trees are not like other symmetries, but are like micro patterns. How many things like this are there with nodes? Infinite?
Well, finite for finitely many nodes. So yes, so Brady, your intuition is correct that trees are like micro patterns. That's maybe a better way to put it. It's like edge times are like patterns in some very. It's like Yeah, actually, that's a good way to. Thanks for the comment, Brady, because that's a good way to put it. It's like a spinal graph is essentially sort of articulating a pattern that your nodes are going to fit in, right? So a tree doesn't have a symmetry in any sense that you can permute anything or there's anything reversible, but it's definitely a pattern that is going to be sort of like rigid, right? In that sense. So if the pattern is rigid, then it will be acyclic. If the pattern has some moving parts like the Rubik's Cube stuff that I showed and things like that, then it'll have some permutation group action going on. But then really the moment that you have a finite number of nodes, then you have finitely many patterns because you always have we are restricting ourselves to connected simple directed graphs on that number of nodes. So that's always a finite family of nodes. They're very big, when you go to 4 or 5 nodes already, the family of this DAGs is huge. Not DAGs, I mean, the family of directed graphs, simple connected, very big already. But that's the idea. Oh, hi Nuno from Portugal. So yeah, it's very cool stuff. I mean, this is difficult, but it feels like proper contribution to the history of computer science. I don't know. I mean, we're doing something important here, I think.
Is it possible that this could be an intractable problem? Or is it just about making things more efficient? Like, there won't be like a solution to solve it like immediately.
Yeah, no, it's not a mathematical problem. It's more like a
implementation.
It's a language design problem. Yeah. It's a computational framework design kind of problem where you want to imagine that your hardware maybe one day actually has an underlying, I mean, as we said before, like the hypergraph processing unit, right? That maybe is optimized to run these kinds of processes internally and things like that. But for now, it's all virtual. It's all sort of at the logic level of how things operate.
Okay, so just hit the 3-hour mark. Is that enough for one day?
Yeah, definitely. No, I appreciate your time, both James and Nick. That I mean, it's extremely useful for me to try and explain, obviously, because I don't understand it myself. So it's important to keep coming to this.
Yeah, so I think so. Where do we go from here? I mean, next week we can just like what would be next steps? Because you've proposed this potential solution. Would it just be like looking at various examples and testing? Like how would we test that this hypothesis is good?
Yeah, I mean, I don't know what you think, Nick, but maybe we should try this idea that just directed graph or like edge spinal graph and try to do canonicalization of the colored directed graphs in that way and see if that misses something for hypergraph isomorphism.
Sure. It's not that hard.
It's simple. It's relatively simple. Yeah. So, and then because if it works, the thing is, if it works, because this has been a big roadblock for me. So if we have a way that we are confident that it's working at least decently well in terms of implementation and efficiency, then there is a lot of work to do on my part. Like I would have a lot of homework to like do taxonomy of types of hypergraphs and make sure that the data structures that we really want are encoded with the right spines and all that stuff. But we really need to make sure that the one job that these things have, which is to actually encode the isomorphism and the pattern matching correctly. Once we have that, and things become much faster. And in 2 weeks, I'll be in Canada for the network science conference, and the summer school. From summer school will be on. So hopefully, I'll be able to present something there. So we have maybe 2 weeks is enough to implement everything, and then we actually have the solution at the summer school, and we do a premiere. We say, hey, we have a general hypergraph isomorphism function here. But yeah, that'll be cool.
Quick last question here. Are you familiar with solitons, oscillations proposed by Marcelo Glazier?
I mean, I am familiar with solitons from my postgrad days, but that's I have a very good friend who just finished the PhD in solitons, but that's about it.
Okay, great. To be continued. Friday we've got a live stream about quantum flux capacitors. I think. I thought those were supposed to have been invented like last year or the year before. Now they're only getting invented 2024.
It's only innovation at the Wolfram Institute.
Okay, it's gonna be a surprise stream. We'll catch you guys
Very
on that
nice.
one. Okay.
Yeah. See you,
Right.
everyone.
Bye for now.